So good morning, everybody. Welcome to the morning session on Wednesday. Wednesday we only have a morning session, so we have especially important people today. So the first speaker will be Felix Otto, and from Leipzig, and he will speak on a variational approach to the regularity of the Monge-Amp equation. Please.
Alex, thanks for yes, on the slides.
This is for pointing and this for skipping forward.
Okay. It's appearing here, but what do I have to do to get it onto the screen? Ah, thank you. Okay. Okay, so yeah. So this is joint work with Michael Goldman from Paris, which is, as one says, in favorable review by the Annals of the UNS, and also I will report on ongoing work with Michael and Martin Huesmann, which is on the archive and which is related to the application and to the matching problem. Okay, so. So the first part will be kind of reviewing or kind of working out a different approach to the famous approach by Caffarelli to the regularity for the Monge-Amp equation. Right away, using the fact that the Monge-Amp equation can be, to some extent, be interpreted as the Euler-Lagrange equation of optimal transportation. So in a certain sense, it's if you're interested in regularity of the Brognier map, it's a shortcut towards at least partial regularity or epsilon regularity of optimal transportation. And the second, if I have the time, the second part of the talk will be related to an application of this type of regularity theory or an extension of this type of regularity theory to what is called the matching problem, which I will explain that. So that's the plan for what I want to do. So so here is just a brief reminder, which probably this audience doesn't really need, of an optimal transportation problem, where here we focus on the simplest possible setting, where we're looking at the optimal transport between two sets in RD. And optimal transport now with the usual Euclidean, square Euclidean distance function. So we're given two sets, omega and lambda in RD, which have equal Lebesgue measure. And we're looking at all maps T that push forward the Lebesgue measure concentrated on omega into the Lebesgue measure concentrated on lambda. And we minimize the cost of shipping the mass, which is described by the characteristic function of omega, into the mass, which is described by the characteristic function of lambda. So that's the well-known optimal transportation problem. And then, as it's kind of fairly easy to see, the minimizer must be the gradient of a convex function. So that's the Brognier map, and formally speaking, at least if it were regular, we would get from this property here that the map has a Jacobian, the determinant of which is equal to 1, which gives rise to, at least in this formal sense, the Monge-Amp equation. And so Caffarelli's famous theory was first dealing just with the Monge-Amp equation, but then that was kind of the paper around 90, and then there was a second paper around 92, I guess, where he argued that this theory can also be applied to this type of optimal transportation problem. And the outcome of this theory is kind of a global regularity result that this map is smooth provided the target domain is convex. And then I think it's folklore or many of you will know that in general, T does not need to be smooth if the target domain is non-convex. Of course, that's obvious if the target domain is not connected, but then you can convince yourself by some continuity argument that even a thin thread which connects the two parts doesn't change the transportation map too much, so that it must retain its discontinuity. Okay, so therefore, even for this very simple situation, if kind of the target domain is not convex, regularity is by itself an interesting question. So here is the main result, which gives a corollary of which gives partial regularity in the situation which I just described. Partial regularity means that you get an open set of full measure on which the optimal map is regular, and it comes from something which in usual regularity, elliptic or parabolic regularity theory, is called an epsilon regularity result. So here I'm stating this epsilon regularity result, which, by the way, now we give a completely different proof, which I'm going to tell you about, which, as it stated, is not a new result. That's something which was proved by Alessio Figali and Kim in, well, almost 10 years ago, and then refined quite a bit by De Filippis and Figali. They're based on kind of the Caffarelli approach. So what's the epsilon regularity theorem stating? So it's probably the first time this notion of epsilon regularity came up in the theory of minimal surfaces, and the theory of minimal surfaces by, where again De Giorgi was probably the main motor behind it. The theory of minimal surfaces states if you already know that in a certain sense around one point the minimal surface is sufficiently flat, then it must be regular. So kind of a mild type of being close to a plane enforces being close to a plane in a very strong sense, being smooth. So that's a typical epsilon regularity result. And in optimal transportation, you have the same phenomenon. So for any Hölder exponent alpha, there exists a threshold, if you want a universal number, small number, which is in principle can be made, which is constructive, which just depends on the dimension d and on this Hölder exponent alpha, so that whenever you have a ball which is contained in both the initial and the target domain, that's not, by an affine change of variables, that's not a big restriction. And you know that in this ball, your transportation energy is below the threshold, and you rescale the transportation energy in the right way to make it non-dimensional. So that means you're looking at a volume integral here, then you take the square root, and then you divide by length. That's the rescaling which makes this quantity non-dimensional. And only on a non-dimensional quantity it makes sense to require smallness, because otherwise it would be in a certain sense an empty statement. So if this non-dimensional local transportation cost is small, then in the ball of half the radius you get what you want, namely you get C2 alpha for the transportation potential, or C1 alpha for the transportation map, which is exactly the type of regularity which you would expect. So that's an epsilon regularity statement for optimal transportation. And again, that's, as it stated, not a new result, but we give kind of a new proof of it, and then we extend the theory in a way which I will explain in a second. But now I want to tell you our variational approach behind this epsilon regularity result. So that's what I want to do now. So and in fact this so the kind of the main difference between the Caffarelli approach, which then was used also by Figali and co-workers, and what we're doing is that we use the variational structure, and we only use the variational structure. So in a certain sense, the Monge-Amp equation is a very peculiar equation, because it's at the intersection between what's called a fully nonlinear non-divergence form equation on the one hand side, and on the other hand, it also belongs, as we all know, to it's the Euler-Lagrange equation of a variational problem. And the Caffarelli theory is based on kind of the first world, that it's a fully nonlinear degenerate elliptic equation, and but still you have the maximum principle at your disposal, and all the regularity theory is based on smart comparison with upper and lower solutions, the so-called Alexandrov lower and upper estimates. I guess some of you have perhaps looked at that. And now the path we take is completely orthogonal to this. I mean, we never use maximum principle. We just use the variational structure, very much, again, in the spirit of the theory for minimal surfaces. And the convenient way to use the variational structure is to appeal to the Eulerian formulation of optimal transportation. And that will hopefully become apparent in a second why you have more flexibility to use the Eulerian formulation. But it shouldn't come as a surprise, because the Eulerian or Benamou-Brunier formulation of optimal transportation makes it very explicit that you're actually dealing with a convex variation problem. And after all, for convex variation problems, things should in principle be good, right? Because one's replacing the seemingly non-convex variation problem by a convex variation problem. So perhaps that's something I can write on the blackboard if I see the chalk. It's here. So the Eulerian formulation is you introduce an artificial time variable next to your space variable. And it's an artificial time variable because the time direction doesn't really matter. And you should think of your initial measure being kind of attached to the t=0 slice. So that's the characteristic function of omega. Here you have the characteristic function of lambda. And then you're looking at all solutions of the continuity equation. So you're looking at the density, or in general a measure, a non-negative measure, and a flux, so a vector valued measure that satisfy the continuity equation in the distributional sense, and so that at time t equal to 1, at time t equal to 0, you have these initial and boundary data. So that in a certain sense defines your admissible set of pairs rho j, and then you're minimizing the space-time integral of this expression here. And if I've learned one thing from Jan, then that this expression here is a convex expression jointly in rho and j, which is very important. Which is a very important observation. Okay, so that's the Eulerian formulation of optimal transportation. So instead of looking in a certain sense of this picture, we look we're thinking of that picture. So that's just an honest reformulation of the problem. And now the main ingredient for our approach to the epsilon regularity theory is the following approximation by harmonic functions argument. So again, that has a lot of similarity with the theory of minimal surfaces, where those who know it know that the main step, or the core step, in proving this epsilon regularity result is to show that you can approximate in energy a minimal surface pretty well by the graph of a harmonic function. And you do that because this way you can borrow the regularity theory of harmonic functions, which we all understand and learn very early, in order to infer regularity theory for minimal surfaces. Now the same thing happens here under the usual assumption that that you're given a ball which is both in the initial and the target domain. There exists a harmonic function phi in the ball of radius 1/2, so that this energy distance between the transportation velocity, j divided by rho, is close to the gradient of the harmonic function, and close in the sense that this energy type quantity is estimated by the energy to a power strictly larger than 1. And the Dirichlet energy of this harmonic function is controlled in the way you would expect. So, okay, so first of all, a result of this type shouldn't be really surprising, because many of you know that that the Wasserstein distance, which is kind of the quantity behind the optimum transportation problem, is in a certain sense a nonlinear version of the h-1 distance. And the h-1 distance, yeah, I mean, is related via the potential to the Dirichlet integral. So, so in a certain sense, this result here reflects that the Wasserstein distance is close to the h-1 distance if the densities are close to 1. But the important thing is that this is kind of a quantitative version of this insight. It's a completely quantitative estimate. And again, the important thing is the fact that the exponent here is larger than 1, which means that if locally your transportation distance is small, then you're even closer to, then your flux is even closer to flux which comes from a harmonic gradient, right? So that's the key idea. And there is very, I mean, again, this parallels minimal surface theory, where there's also kind of a very explicit estimate of this type. One can, in minimal surface theory, there's also a more compactness type approach to this, but on the other hand, it can also be kind of made explicit like this. So that's really the key observation. And from then, once you have this lemma, which I want to explain a bit more, then the usual machinery in order to get an epsilon regularity result kicks in. So that's, I guess, on the next slide. So, so once you have this theorem, perhaps I can, is there also, write it down here. So again, so the statement is that you look at the difference between the flux and rho times the gradient of a harmonic function. You look at the usual kinetic energy expression, 0, 1, B1. This one is estimated up to universal constant, which only depends on dimension, by the transportation distance in the B2 ball to a power strictly larger than 1. So that's the that's what I call the lemma. Yeah, I'm sorry, but there's no there's a that better? Now this also gibt auch seinen Geist auf, as we say in German. That I already used. I think you have to live with this. So, so that's kind of the core problem-dependent assumption, and then you put it into the machinery to get an epsilon regularity result, which is an iteration. So for that, it's better to go back to the Lagrangian level and to introduce the following modification of the energy, where you allow yourself an affine transformation. So E of R would be the properly rescaled energy in a ball around the origin of radius R, and now you allow yourself an affine transformation Q and a shift vector B. And you don't just look at t minus x, but you look at this type of this type of transformation. And then you can rephrase, using regularity of harmonic functions, you can rephrase this lemma in the following way. If your energy is small on radius r, then for any theta, for any fraction which is very small, the energy on a much smaller radius is even smaller, provided you kind of change coordinates. You introduce this tilt, which is given by the matrix Q and by the shift vector B, in the sense that you get the theta square here, which comes from kind of using regularity on harmonic functions, and you get the superlinear term, which comes here from the right-hand side. And you know that you didn't need to transform much. So so again, for those who know minimal surface theory, that's exactly the same thing. If you have flatness, then the flatness improves if you go to a different set of coordinates. You have to tilt it, and then it gets flatter, and then you can reapply, and it gets even flatter in kind of an even different set of coordinates, and so on. So once you have this here, you can put it into what's called a campanato iteration to get the regularity result. So, but this, in a certain sense, is the standard approach to regularity, and it's not, in the end, it's not so much different from the usual thing. Perhaps the only thing which is still specific to optimal transportation, or the Monge-Amp equation, is that optimal transportation has the affine invariance and not the Euclidean invariance. So, but that's also crucial in Caffarelli's approach, that the Monge-Amp equation is affine invariant, and that plays a role here, that if you even do a non-Euclidean change of variables, you preserve the structure of the problem. Okay? So now the, thank you very much. Now the, I don't know whether it's still worthwhile doing this. But now the extension of this problem, and in a certain sense that may show the power of this variational approach over the maximum principle based approach, is that it holds also true if you're replacing your initial and your target measure, which here were kind of characteristic functions, by general measures. Oops, no, that was okay. And even in this situation, when you don't have any regularity of the initial and target measure, so you've just given two measures in RD which have the same mass, and you look at the as usual as we did before at the Eulerian version of optimal transportation, then you still get a result of this type. And the convenient way to phrase it is to introduce kind of two size measures. One's the kind of data size measure, so that measures, D measures how close in the right topology, in the Wasserstein topology, in the square of the Wasserstein distance, the initial and the target measure are close to the Lebesgue measure, and E is as before, our local energy. And still you have now I've written it in a less quantitative way. You have the same type of result, that for any small number tau, there exists a threshold such that provided your D and E is below that threshold, there exists a harmonic gradient, so that optimal transportation is close to the harmonic gradient with an estimate which is tau, which is this tiny number times E, plus the data term. And that's again very much like in elliptic regularity theory, that you can show that in the energy norm, your solution is closer to a simpler problem, in this case the Poisson equation, with something which only depends a little bit on what's outside, and depends quite a bit on the local right-hand side, right? I mean, it's this, the fact that you only need a little bit of this energy here, which allows you to kind of localize in a certain sense, to show that everything that's happening far away doesn't really matter, and that's the main ingredient for regularity theory. So, so that's exactly the type of result we need for the matching problem, because in this case, the measures are, one of the measures is a Dirac measure, so highly irregular. Okay, how much time do I still have? Okay. So, so now what I want to do is I want to first give you a little bit an ingredient, what's behind this type of result, this approximation by harmonic gradients, and then I want to tell you a bit, what needs to be changed if you want to consider a kind of more general or completely general initial and target measures, and then I want to go to the matching problem. So that's the plan.
So a question.
Yeah.
So where do you use the assumption of the target from the convex in all this?
No. But that's already the case in the almost in the partial regularity result of Figali and Kim. That, of course, the interesting case is when the target domain is non-convex, because otherwise you could immediately appeal to Caffarelli and say everything is fine. So they want to have they want to say that even if the target domain is non-convex, in a certain sense you can say something about regularity, which is partial regularity, and it's built on this epsilon regularity result. And so so it's a completely local approach. You don't care for how things look at the boundary or far away. Does that answer the question? Okay. Okay. So so the ingredients for the lemma are the following. So here again is I recall you of the main part of the lemma, this kind of superlinear estimate of the energy difference between optimal transportation and the Poisson equation, superlinear in the sense that this exponent is larger than 1. So how do you get this? Well, I mean, first of all, you have to construct so it's, as I said, a completely constructive proof. So you have to construct this harmonic function. So how to construct this harmonic function? By imposing boundary data. And what are the most natural boundary data to impose? It's more natural, since it's about transportation, it's more natural to think about fluxes, so Neumann boundary conditions, instead of Dirichlet boundary conditions. So you should impose Neumann, or it's natural to impose Neumann boundary conditions. And what Neumann boundary conditions should you impose? Well, in a certain sense, since you want to compare gradient of phi to j, you should, it's natural to take the same boundary conditions for j and gradient of phi. But now you run into a slight technical difficulty in the sense that the j, this flux, is a function of time and space, whereas the PDE, this boundary value problem, of course, just sees space. So the most natural choice is to say, well, let's take the time average of, here we have somewhere the boundary, dBr, and we take the time average of, of the flux boundary data of J as our flux boundary data for the harmonic function. And then, as it's, many of you will know, it's good to kind of choose a good slice. I mean, we have some freedom of where, since it's an interior regularity result, we have some freedom of where we put the radius, and we choose the radius in a smart way, and we choose the radius in such a way that the transport restricted to this sphere is of the same order as the transport on the ball. So that can always be done. So this is how you get the harmonic function, and then essentially relies on two observations. One is kind of an orthogonality, which is very much like in linear variation or quadratic variation problems, that the that the distance, the energy distance to the minimum, is estimated by the energy gap. So how well can you approximate, I mean, that's the quantity we're interested in, and that in the end is estimated by the difference between the actual nonlinear transportation distance and the Dirichlet integral. So that's what if we had a completely quadratic problem, this would be an identity, but luckily, since, and there, this is a huge simplification, because then we know that this rho by McCann's displacement convexity is always less or equal to 1, and using this clear inequality, we get this clear inequality. So that's something we need to substitute when we look at more general measures. So that's the orthogonality. That's a simple integration by parts. And then the key part is to construct a competitor, right? I mean, in the approach to regularity theory in variational problems is always by constructing something that could potentially be smarter, and then using the fact that it can't be smarter. So so that's the key step. We're constructing a competitor rho tilde j tilde, which has the same boundary conditions as rho j, and where the transportation energy minus the Dirichlet energy is of higher order in the sense that it's estimated by this superlinear expression of the flux. So those are the three steps of the regularity theory. And the main the main step is how to get this competitor, and there one needs a boundary layer construction, because the main issue is really how to go from the flux boundary conditions F, which is the normal component of J, to its time average. And so that's the difficulty which arises there. And in order to accommodate, in order to go from F to F bar, or in order to accommodate for the difference between F and F bar, you need a boundary layer construction, and that in the end reduces to a trace estimate. And this is a little bit reminiscent of an argument Giovanni Alberti, Ustum-Choksi, and I used in kind of a different problem of calculus variations, and here we're using kind of the same tool. Okay, so that's the that's how to get it in the in case of the lemma, and now in case of this proposition, we're more ambitious, and now we have kind of two general measures, mu0 and mu1, and we claim something very similar. Is estimated by tau times E plus a constant which depends on tau times D. And E being the energy, D being the data term. We run into some interesting questions. So here's the definition again of the data term and the energy. And the first difficulty is that in this case, rho and J are really just measures. Before we knew that because of McCann that rho is J is an L2 function and rho is bounded by 1. So now we're kind of in the very general context of optimal transportation, where these objects are just measures and not L2 functions. But then it's a little bit difficult in terms of the boundary values of our elliptic operator. We cannot just take, we lack the estimates to do something if it's a measure, and there we need kind of to approximate F bar, which is a measure, by an L2 function. But again, optimal transportation itself gives us a good way of doing that. There is kind of an intrinsic nonlinear way of doing such an approximation, which in a certain sense is explained by this picture, by coupling the transportation from the initial measure to the constant, and from the initial measure to the target measure, by looking at all the trajectories that leave the domain. That's in a certain sense which gives rise to F, and connecting them to some density on the bottom and projecting that density on the boundary. That's what the G is, and for this G you get provided you choose the right radius, you get a nonlinear approximation argument in the sense that that the L2 norm of this G is controlled, and the distance of G to the F, which you really want, is superlinear. So, and I think in the interest of time, I'm looking again at the chair to tell 15 or 15. Yeah, it was kind of clear that it wouldn't be 15 minutes again. And okay, so there are a couple of I mean, from the point of view of optimal transportation, there are a couple of interesting challenges in the general case, which in a certain sense can be nicely done intrinsically. You need an L infinity estimate. That's actually the only place where you ever use something on some structural property on the optimal on the solution, like in this case monotonicity. You need to introduce boundary layers next to initial and terminal layers next to boundary layers. But then it again reduces essentially to the same two ingredients we had before, a construction and an orthogonality observation, where now the orthogonality observation becomes more subtle. So instead of this being less or equal to 0, thanks to McCann, one has to estimate it. But this can be done. Okay, so Martin Huesmann and Michael Goldman and I did this kind of generalization because we were looking at this problem of matching, or I mean, to be honest, perhaps it was also a bit the other way around. We thought we had this nice regularity theory, and now we were looking out for a good application, and this matching problem kind of came quite naturally to our mind. So I recall to you the matching problem. So you give yourself a kind of a large torus, where L is the linear size of the torus. You throw randomly the right number of points into the torus, uniformly distributed. And the number of points is such that the typical distance between the points is of order 1. So for the experts, that's kind of a poor man's version of the Poisson point process. In the Poisson point process, you would also make the number of points random, but concentrated around that number. And then you look at the this sum of Dirac measure. So this type of empirical measure, if you want. And you're interested in looking at the optimal transportation problem from the Lebesgue measure, which, because you looked at this microcanonical ensemble, has exactly the same mass as the Poisson measure. You look at the optimal transportation of Lebesgue into Poisson, and you're interested in the hydrodynamic limit. So you're interested in large domains. So, so here again is the setting of the problem, and so this is I think a problem which computer scientists have looked at, but then as I was told by Luigi, also kind of physicists here in Pisa got interested into this problem, and in particular Parisi, who I think is quite famous theoretical physicist. Got interested in this problem, and they kind of had this this vision that which in a certain sense is a little bit in line with this type of result that oh, now I'm gone, that's good, that in fact the optimal transportation map should be close to the identity plus something that solves a Poisson problem. And since the target measure, in a certain sense, can be roughly assimilated to the uniform measure perturbed by something which on large scales behaves like white noise, the right-hand side of the Poisson equation should be white noise. And that, of course, is something which you can characterize completely. You can relate to so the gradient, in a certain sense, is a little bit like the Gaussian free field. So this is an object which now you understand very well. And therefore, they said, well, this transportation distance to leading order should be approximated by the Dirichlet integral of the solution of this stochastic partial differential, linear stochastic partial differential equation. And then you see a phase transition at 2 dimensions, very much like you're used to from the Gaussian free field. Namely, if you're in high dimensions, at least on large scales, you don't have an infrared divergence, but in dimension 2 it's borderline. You have an infrared divergence, and it grows logarithmically in the size of the system. So in a certain sense, the 2-dimensional case for this problem is the most interesting. And that is also borne out by a result of Martin Huesmann and Theo Sturm, who showed that if you were right away looking at the infinite volume limit, and you were asking the question, is there a stationary shift covariant optimal transportation? So in a certain sense, like the stationary corrector or the stationary gradient of a corrector in stochastic homogenization, they made the point that this can only be if the dimension is strictly larger than 2. So only if you don't have this infrared divergence, you can hope for having kind of a simple functional analytic approach to this problem. And on the other hand, Luigi Ambrosio and many of his co-workers and new ones kind of looked at the 2-dimensional case from the point of view of energetics, and in this result got a kind of confirmed the heuristically predicted energy scaling and logarithmic divergence of the optimal transportation cost. And now in the recent work with Federico Claudo, also kind of on that macroscopic scale closeness of the optimal map to the Poisson problem. Now what we hope, or what we in a certain sense did, is a similar type of result, but on the local scale. So in a certain sense of kind of looking at the homogenization limit, we want to look at the fluctuations. We really want to look at how on the scale of the distance between the points, what can we say? So kind of in a certain sense looking at the same type of question, but from a finer perspective. And essentially, so one of the main results, so in fact this is already posted, one of the main results is that if you look at this matching problem, and you look at larger and larger sample sizes, but then you zoom in locally, let's say around the origin, and you look at a radius that's essentially large, but might be large, but of order 1, so local, not global, then you can show that this globally defined optimal transportation map is close to a shift in the local L2 sense, and the shift itself grows logarithmically in the system size L. And while we are not yet in the position, but I hope we'll be eventually, to get the right power of the logarithm, which should be logarithm L to the power 1/2, we get as an upper bound for the shift, we get this logarithmic behavior. And then equipped with this behavior, in a certain sense, we can give in a certain weak sense the result that indeed also in the 2-dimensional case there exists a limiting object, but the limiting object, it's not the map T that's shift invariant or stationary, but it's the gradient of the map T that's shift invariant. And those who know stochastic homogenization, it's a little bit like for the corrector in random stochastic homogenization in 2 dimensions, the corrector itself is not a stationary object, but the gradient of the corrector is a stationary object. And here it's the gradient of the transport map that's a stationary object. And so that's for this result we exactly need the this extension, this proposition which I stated earlier, which extends the lemma to a general target measure. So in this case, we just needed the target measure to be general, not the initial measure, but we can go the full way and consider both as general. So that's the application which we want to pursue of this type of variational regularity theory for Monge-Amp to the matching problem, which I wanted to point out at the end. And I think that my time also should be over. So the first part was kind of a more classical situation where we reproved by variational methods the known results by Figali-Kim, Figali-De Filippis, and the second part is an application to this matching problem where we hope eventually to be able to say more things. Okay, so that's.
Thank you very much for the lecture. This is open for questions, discussion.
So the predictions of Caracciolo and Parisi in dimension larger than 2 give the subleading terms. They have a specific expression. Do you think your method can give something on dimension larger than 2 also?
So I would say our aim is different. So in the recent work of Ambrosio and Glaudo,
Yes.
Glaudo. They actually, so in the two-dimensional case, they give kind of even finer statements on the energy convergence, and so that's not what we're shooting for. I mean, we want to look at the microscopic scale, right? That's I mean, the analogy is we want to look at the fluctuation scale. I mean, we're not interested in we're not just, I mean, that's very interesting, but our focus is not on the on the homogenization scale, on the macroscopic scale, but on the fluctuation scale. So that, in a certain sense, is more ambitious. So and that's what our methods are target for, because what this type of regularity theory tells you is that, in a certain sense, the far field doesn't matter, right? It's the local right-hand side that matters for your regularity. That's, in a certain sense, the core of all elliptic regularity theory, that you manage to rule out, to some extent, the far field. And so, therefore, if our methods have an impact on matching, then it's on the fluctuation scale, not so much on the energy scale and getting fine corrections to the energy.
Okay.
But this being said, we so far what our results don't give anything interesting in dimension larger than 2.
Other further questions or remarks? This is not the case. We thank the speaker once again. And we will have a 5-minute break and start 5 before 10. So let's start the second part of the first session this morning. The second speaker will be Benedetto Piccoli from Rutgers University, and he will speak on evolution equations and control problems for measures. Please.
Thank you very much. So thank you, the organizer, for this great opportunity. Usually, my motivation for using some tools of Otto transport comes from applications. Applications where we have large systems like crowds or vehicular traffic, and we are trying to understand the dynamics and also possibly to control them. So it's a work with a lot of people. I will mention more during my presentation. And usually I talk to more applied audiences, and in that case I start really from the application, explaining a little bit the phenomenology, the possible models, and then towards the end going to more theoretical aspects. Since this audience is different, I will do exactly the opposite. So I will start talking about a new idea on how to define some evolution problem for measures. Then I will move to some remarks about control approaches. And finally, at the very end, I will show some application. So let me start with the first part, that is evolution equations. Obviously, there are a lot of already well-defined and powerful tools to define evolution of measures, optimal transport and gradient flows and many others. And this proposal that I'm doing in this first part is really how to take most of the ideas from ordinary differential equations and trying to push towards measures. So in that sense, I'm going to use pretty simple tools. So the first point of view is, OK, let's reinterpret a little bit what is an ordinary differential equation or a vector field. So obviously, a vector field can be seen as a map that to every point associate a vector in the tangent bundle, or directly the vector field as a section of the tangent bundle. And we can use the natural immersion of Rn into space of probabilities over any Rn, identifying a point with the Dirac mass center at that point. So if we make this identification, then a vector field is just a map that to every Dirac mass on the base associate a Dirac mass in the tangent bundle. And the only requirement we have is really that it projects down correctly. So we are not going to apply a vector in a different point. We can immediately then decide to generalize that not to only Dirac measures, but to any one. So we can define a probability vector field as a map that to every probability measure on the base space is going to associate a probability measure on the tangent bundle. And the only requirement is that it projects down nicely. So if we project down on the base, we are going to get the original measure. And the interpretation is here. I'm thinking like, the velocities corresponding to the fiber over a point is like in optimal transportation, a way of prescribing the directions along which our mass should move. So formally, we defined in this way. Probability vector field is a map from the space of probability measure to the space of probability measure over the tangent bundle so that it projects down nicely. The pi1 is the projection over the base. You recover back your measure. I will discuss later regularity. But once we define that, obviously, we have a corresponding ordinary differential equation or measured differential equation that is just written in the following way, like we write an ODE. So the derivative of the measure is given by this probability vector field. At this point, the solution should be interpreted in weak sense. Obviously, we are talking about measures. So this is a reasonable definition of solution. When we take a test function, we look at the derivative of the integration against the test function. A curve in the space of probability measures is a solution if this derivative is equal to this term, that is the natural one, right? So we have the gradient of f scalar product v, and we integrate with respect to v of mu, that is a measure on the tangent bundle, in the variables x and v. This definition is by itself very weak. So if you want to deal with this type of approach, we're going to have easy time to define to find existence of solution, but much harder time for uniqueness. And that's exactly what's going to happen. So let me make some observation here. Well, first of all, you see it's very weak. And in particular here, you see what matters is just the average, right? So in particular, if you would average over the v variable, you obtain exactly the same expression. So in particular, this concept of solution is blind with respect to averaging. If the averages coincide, they're going to be exactly the same type of equation. So let me make two examples that show the problem of uniqueness and different ways in which you can use this tool to define evolutions. So the first example is the following. Assume that by this integration, we have a constant vector field. Say we are in Rn. OK, I will explain all the theory in Rn, but obviously some concepts generalize nicely to manifolds. So assume you have a probability vector field that is constant on the fiber. This is a fixed probability measure. Then you just average and you get some vector v bar. And then any solution to this equation is just the translation with constant speed. So in particular, you see that what happens there in the fiber really doesn't matter. What it matters is just the average. In particular, if you take a v bar to say be the sum, well, 1/2 of Dirac mass center in -1 and 1/2 in +1 over the fiber, well, nothing will happen because the average is 0 and every solution will be just constant. Let me give you a very different example. Would be a one in which we use the global properties of the measure, so really opposed to this one. So take a simple example in R. We define the barycenter as usual, and then we do the following trick. Essentially, we move, say, the left part to the barycenter of the mass with speed -1, the right part with speed +1. So if the barycenter, if the measure of B of mu is 0, is just this one. You know, you move to the left when you are to the left of the barycenter, you move to the right when you are to the right of the barycenter. Now, if you have an atom exactly in B of mu, you need to define exactly what happens in B of mu, and this obviously is you split the mass exactly as it should go, so that the first half again goes to the left and the second half goes to the right. Now, here we would like to say that the natural solution to this probability vector field should be exactly the one. If we start, say, from a Dirac mass, we should see half of it going left and half of it going right. But obviously, also the constant solution, the one that doesn't move, is a solution to this, is a trajectory to this probability vector field. So immediately we see this phenomenal lack of uniqueness. Again, if you take the constant one that correspond to a Dirac mass center, half Dirac mass center +1 and half Dirac mass -1, you have the constant solution. But also to this probability vector field, you have the constant solution. But there is another natural solution that would be the one splitting the mass to the left and to the right. So what I want to show is that using a scheme that is essentially the natural generalization of an Euler type scheme for the ODE, you're going to be able to recover these type of solutions, and not only the one that correspond to average in everything. So let me first put some conditions on the board under which this construction will work. I will use a very simple setting. So I'm considering measures with compact support, and I'm assuming sublinearity with respect to the support. So if you look at the maximum on the support of the measure mu, and you look at the maximum velocities of mu, you have a linear sublinear bound. Okay? So the support grow at mass sublinearly with respect to the support of the measure mu. The second condition is continuity with respect to the Wasserstein matrix. I'm using W1 here. Okay, so the P equal 1. I put the topology on Rn and Trn given by the Wasserstein distances. Under these conditions, we can construct an Euler type approximation that I call lattice approximate solutions. These are constructed in the following way. So the idea is very simple. You construct a lattice in the space and time, and you want to move your measure just on this lattice. So what you do is that, for instance, you start with the initial condition that is just a Dirac mass, and you look at V of mu 0, that at this point is a probability measure concentrated over the point where mu 0 is centered. You discretize that, you introduce grid points also on the fiber, and then you choose in a particular way. Say that you choose the size of the fiber discretization 1 over n. Similar, you choose 1 over n in time and 1 over n square in space. If you do that, then naturally, if you will move along the vectors corresponding to this discretization, you will end up in points of the grid. So your measure, your initial Dirac mass will be just split in few parts using this discretization. At this point, you can just go on. So you look at the measure mu1, that is a finite collection of Dirac masses over this grid. You look at V of mu1. This is V of mu1 is concentrated over these points. You again use the same discretization. And if you use the same discretization and you move the masses, again, they will just stay on this lattice. And as you can imagine, then the idea here is just simply send n to 0 and try to recover solution in that way. You immediately understand that if we use this type of scheme, the solution to the second probability vector field that was showing, the one related to the barycenter, will exactly move the mass to the left and to the right. This will be indeed the solution for any n, just moving along this grid the masses. So if, on the contrary, we use the first vector field, the one I said that by this integration is constant over the fiber, then this limit will be just a constant solution. It's very easy to see. This is giving rise like a binomial distribution. And when you send n to 0, this goes back to concentrate around the Dirac mass center at the initial position. On the contrary, if we look at the second probability vector field, these solutions will be constantly for any n, indeed, just moving mass to the left and to the right with speed -1 and 1, and we will be just discretized in time, but nothing will happen. So you see that immediately this scheme is selecting different solutions. In the first case, it's selecting the constant one. In the second case, it's selecting the one splitting mass. So this is a general fact, and we can build up a theory on this. So first of all, let me give the formal definitions, but you already got the idea from that cartoon. So you fix 1 over n, and you define first two operators. The first one is discretization over this grid. So whenever you have a measure mu, you replace with a finite sum of Dirac masses. You put an n here, but since we have compact support, for n big enough, it will contain the support for every, say you fix a time horizon big T, and the support will be contained in this interval. So no problem with that. And you just center the mass over this hypercube at the point xi. Similarly, you define another operator that is on the tangent bundle when you want to discretize V of mu. And similarly, you will have grid points belonging to the lattice in the tangent bundle. And again, you will have an hypercube, and you will concentrate the mass there. And this delta now is centered at base points and discretized speeds. Once you do that, the definition of solution, lattice approximation solution, is very simple. You just have, say that you arrive at the step L, and you won't define the step L plus 1. You just look at V of mu n L delta n. Okay, so the discretized solution, you look at this probability vector field, and you discretize along this lattice. And then you go to the next step just by moving every mass that was at the point xi by some delta n Vj. So the definition is very simple. And what you can prove is that under these two conditions, you can pass to the limit. There are subsequences that converge, and they converge to a solution to this measured differential equation. As I said, existence is easy, and this is just one possible way of achieving it. But the more interesting question is, can we come up with some form of uniqueness? And uniqueness will be discussed at the level of semigroup. What I mean is that at the level of single solution, obviously, we cannot hope to have uniqueness. So the idea is the following: to put some condition over your probability vector field so that you will have a form of uniqueness in terms of either generating one semigroup of solutions, so uniqueness in this sense, or uniqueness also of the semigroup itself. And the condition that you can give in terms of Wasserstein distance, a Lipschitz type condition, is expressed in terms of this operator script W that is not a distance. So the idea is the following. You want to measure somehow the distance between two probability vector field, or better to say two probability measures over the tangent bundle. You look at all at the optimal transportation problem, but you see you restrict it to those transference plans that project well on the base, in the sense that if we project over the first or third component, that is at the base component of these two measures, then this should be optimal. So we allow ourselves to transport over the fiber, but only making sure that over the base we are using an optimal one. Otherwise, if you use just the Wasserstein distance over the tangent bundle, the optimal one could mix things and move points wherever. That would not make sense much from the evolution point of view. So what you are doing is you are restricting this in this way. And because there is this restriction, this is not a distance. It fails the triangular inequality. But you can state a nice condition in terms of this quantity. So you assume that whenever you have uniformly bounded support, there is a constant so that this quantity satisfies a kind of Lipschitz estimate. So this W of V mu V nu is estimated in terms of a constant and the one Wasserstein distance between the base measure. So this pretty natural condition gives rise to a semigroup. So if we have this condition, the H1 was the sublinearity, and this condition that implies the continuity with respect to a Wasserstein distance, then there is a semigroup of solutions, a Lipschitz one, and this is obtained passing to the limit in the lattice approximate solutions. So at least we have some form of uniqueness in the sense that we can isolate solutions that depend nicely on the initial data. But we can indeed isolate also a semigroup if we somehow prescribe how solutions to finite sum of Dirac masses should look like. So the idea is the following. We call Dirac term essentially a map assigning a small time evolution for finite sum of Dirac masses. So D is the set of finite sum of Dirac deltas, and the Dirac germ is a map assigning, you see, a small curve, a curve defined for small times, that is solution to our MDE, and so that the time of existence is uniformly positive for uniformly bounded support. So in particular, one could imagine that you can select solution looking at lattice approximate solution or giving other conditions for selecting solutions to Dirac masses. And what it matters is just select those solutions. If you do that, then you define a Dirac semigroup. Well, a semigroup that is compatible with this small time evolution, in the sense that if we look at the small time evolution, this the semigroup trajectory stays close to this evolution in the sense of t squared for small time. And if this is the case, then you know, we do recover uniqueness. In the following sense, again, we assume that we have this assumption H1, and we have an assigned Dirac term. Then there is at most one Lipschitz semigroup compatible with gamma. And now we go back to condition H3. If we are able to find a unique limit, for instance, of these lattice approximate solutions, like it was for those two examples I gave, then there exists a unique Lipschitz semigroup that is compatible with the lattice approximate solution in the sense that they are closed for small time. And here I close a little bit the circle in the sense that, again, you need to check these lattice approximate solutions. If they converge to a nice unique limit, then you're going to have the existence of a Lipschitz semigroup and a unique one compatible with those solutions. So you get uniqueness, but at the level of semigroup. So this is a little bit a presentation of this part, and let me switch now gears and discuss about control problems. Again, from the application point of view, we are interested both in coming up with models that try to capture the reality of these large groups, but also to control them. And controlling them is very difficult. So I will show you first a possible optimal control approach, and then an application with a theoretical result. So the first part will be like a distributed control. And this is an approach that we worked out with Giulia Cavagnari and Antonio Marigonda. Indeed, they really built up the theory, and this is a further application to minimum time problem. So the idea is the following. You have a transport equation, and you assume that you can control your v of t. So you can control the directions along which you are going to move your mass, but you will have some restriction. You will be allowed to move your mass just along trajectories of a fixed differential inclusion. So this could be a given, say, control system that is given to you in the application, and you are going to try to find the optimal way of the moving mass, but having this constraint. So you cannot use any speed, but only the one related to this differential inclusion. So this is a little bit difficult to read, but let me point out the main ingredient. So once you have assigned this set-valued map, the trajectories are going to be solution to a transport equation where this nu will have a density with respect to your measure mu that is within the bounds that you gave. So belongs to this multifunction given f. And you call this a trajectory, and using superposition principle, Ambrosio, Gigli, Savaré, and other, you can represent your solution exactly along trajectory of this vector field. So the idea is that you can define control problem and optimal control ones by using this framework. So what Giulia and Antonio and others did before were addressing very natural problem like Boltzmann problem. And what we did is to modify this approach to address time optimal control one, that in this case are slightly different. And the slightly different approach is because you need somehow to introduce a clock related to your trajectory that is telling you that your time is going down. So we define a clock trajectory as a pair so that you have a usual trajectory as defined in the previous slide, and this clock that is like a countdown. So this clock works in the following way. If you have a representation eta, you see what we are saying here. Well, phi is a test function. This is the indicator of the complement of the target. So it means that you are still active in your clock as long as you don't reach the target. And this terms is telling you that your clock is just going down linearly. So in other ways is the following. If you fix one trajectory in your representation and you look at this f0, this is going down a long time. And it goes to 0 exactly when it reaches the target. If you use this clock trajectory representation, then your f0, that will be an integrable function with respect to mu0, will indicate exactly the time that you are going to take to reach the target. So if you do that, you can run the usual program of dynamic programming principle and Hamilton-Jacobi-Bellman equation. So more precisely, you have the following. Consider the minimum time of your original differential inclusion, and then you can define a minimum time for measures just by integrating that. Well, obviously, you have some integrability assumption that you need to state there. Then you have a dynamic programming principle in the following sense. You look at your minimum time at initial time, and you look at what happens when you move along trajectories, and you have the typical DPP inequality. So at time s, if you sum s plus the minimum time of the measure you reached, this is going to be the inequality that you satisfy. And if you look at optimal trajectories, then you will have an equality instead of an inequality in this relation. OK, so it's disappeared, but then you have Hamilton-Jacobi-Bellman equations. You can define appropriately an Hamilton-Jacobi-Bellman equation, define an Hamiltonian, and looking in this case at P2 and W2 as natural object to define viscosity solutions. Let me skip a little bit of details here. I mean, defining the functional and in which sense is viscosity super and sub solution is a little bit lengthy, but I would like to stress that an important point is that you can carry out the whole program. What I mean is that you can get also regularity in the sense of the 2 versus time distance, and more precisely W2 geodesically semi-concavity. So if you have the typical, well, this is like a Quine-Jurjevic condition. So if you have some direction that points inside your ball of radius r, then you are going to get the strongly W2 geodesically semi-concavity of your minimum time function. So the message is more or less the following. You can carry out the usual program that you do in optimal control if you define evolution of measure according to this setting. And there are many other possibilities of defining control problems. One possibility would be to resort to MDEs and generalize naturally to differential inclusion in that sense. But what I wanted to talk next is really what can you do in applications. So imagine that you have this large system like, for instance, vehicular traffic, where you want to control this huge system where you have thousands, if not millions of cars. And typically there are ways that traditionally people try to do, like maybe related to this type of mathematical approach in which you have entry points, speed limits, and you have somehow a control that is a general one that applies to all particles. But then there is a new perspective that is coming up with autonomous driving. So autonomous and connected driving open the possibility of doing more a Lagrangian-based control. So a control where you control a small number of particles, and the idea is that control a small number of particles, you want to influence the overall dynamics of traffic. So let me show you an idea here on how to do theoretically, and also an application of how we started to address the problem. So I cannot help but making a little joke about what is optimal transportation, because I work a lot with transportation engineers. And so when you talk about optimal transport or optimal transportation, obviously what they typically understand is that, well, optimal means the best, right? Somehow in some sense. And transportation, well, transportation is traffic, right? Is traffic, or anyway, more general public and private transportation. So if you talk to civil engineers, optimal transportation means you are going to optimize traffic. So what I want to show here is exactly an attempt to optimize traffic. But first, before showing you the applied result, let me mention a possible theoretical approach that could work here. This was developed with Massimo Fornaziere and Francesco Rossi. So the idea is the following. You want to define this control, say, on a small number of cars, right? And then you want to pass to the limit. So when you pass to the limit so that you control a very large traffic system with small number, you are going to have a lot of problems, because your control will, when you pass to, say, a mean field type limit, your control very likely could become singular. And Massimo and collaborators showed a lot of results in that direction. So one possible idea to overcome that difficulty is to use a sparse control, in the sense that you assume that you always control a small number of particles. And this small number of particles, if you think to the traffic applications, correspond exactly to those small number of connected and autonomous vehicles. Now, as you know, autonomy is taking different paths. So after some accident that happened, some big operators are becoming more cautious about using a completely autonomous car. But what is going on is that an increased autonomy over cars is coming to the market soon. So the idea mathematically is the following. You have a system that could represent a lot of different dynamics, like Cocker's mail, or for people knowing traffic, follow the leader. You could represent your system like, well, a second order system, so the relative position speed. The relative speed is given by some term, a convolution with your empirical measure that may represent many different functions, but again, including Cocker's mail, follow the leader, and many others. And you separate your population in two parts. A first group are the leaders. So they follow, you see, a dynamics that involves and this population is the follower. So this population is small and this population is big, and you're going to pass to the limit in the big population. This small population you assume you can control. And the bulk population, the big one, you cannot. So the idea is, okay, we will keep controlling this small population, and we will send the big population to infinity. And we want to still get some properties so that we can solve the optimal control problem in the limit by approximating the problem with some discretization. So you are going to compare these two systems. The one is the still discrete one, and this one is the limit one when you pass to the mean field. And they behave well in the following sense. You can define some functional. For instance, you are minimizing Lagrangian cost plus a constraint for sparsity. and then you have gamma convergence of the approximating functional to the limit one. So in particular, optimal controls converge weakly. And what I'm going to show now is a real application where we're solving this problem. So we were taking a small population of cars and we were trying to control them using a small number of leaders, well, indeed one. And this we did through engineering work with that. And the idea now is that we are trying to pass to the limit in this sense. So this was done mathematically with Massimo and Francesco. And now we are trying to do with real cars. So let me show you what we are trying to optimize. And this first experiment showed that we can try to control. So I have to do a little bit of introduction. There is a very well-known phenomenon in traffic called stop-and-go waves or traffic phantom jams. And this is the following. This is a very famous Japanese experiment. They put cars on a ring road that are equispaced and going at the same speed. And even if they start at the same speed, there are oscillations in human driving. Especially, there are different ways in which we react to the car in front. So if the car in front brakes, we can have different reaction time. And this causes this phenomenon. If you wait a little bit, the distribution of cars will not be any more homogeneous. There are stop-and-go waves. So cars come almost to a stop, and then they reaccelerate. This is like exactly a shock wave. And you see the point where cars essentially go to a stop, travel backwards in time. So as it's predicted by conservation laws model to vehicular traffic. So this phenomenon is very well known and is ubiquitous in the sense that it is observed in this experiment, but is observed obviously also at the level of highways. If you drive usually on highways, you probably encounter this type of phenomenon called stop-and-go or traffic jams, traffic phantom jams. They are called phantom jams because people do not understand really where they are coming from. Well, they obviously comes from the oscillations in the driving style, but it's very difficult to predict them. Well, again, you can make some prediction that they will appear, that they will be stable, but when they will appear and the dynamics is not so easy to characterize. So what we did is we studied this phenomenon from the point of view of seeing which type of impact do have these waves. And then finally, we tried to control them with autonomous cars. So the experiment I'm going to show now is an experiment in which we were still using a ring road setting. Oops, sorry. Yes. A ring road setting like the Japanese experiment, but we were trying then to control. So this experiment was part of an NSF project involving various universities, University of Illinois Urbana-Champaign, Rutgers, Temple, University of Arizona, and then at the end of the project also Vanderbilt. Again, the main idea is that we are going to observe stop-and-go waves. We are going to measure the impact that they had on traffic, and then we are going to try to dissipate them using a single autonomous vehicle. So let me show you the video. This is an experiment that was run in Arizona desert in July, so it was pretty hot. And this is the beginning of the experiment. So you see there are, let me stop immediately to tell you a little bit what's going on here. These are cars going in the ring road. You see there is one car with a big arrow, and this is the autonomous car. When the arrow is black, the autonomous car is in a human driving mode. So it's, there is a pilot on board and it's driving like the other humans. When the arrow will become red, then the car will be under autonomy, and so we are going to apply some control to dissipate these waves. Here there are a lot of numbers and graphs. Up here we will measure, depending on how the experiment is going, various things like the standard deviation of speed. We will look at fuel consumption that was measured directly with the onboard technology on each car. We are going to look at the braking events, so the number of events per vehicle per kilometer. So we define braking events when we have a decrease in the speed of the car of at least 1 meter per second and over a time span of 1 second. So it's a big break, and it's well known that there are relationships between these big breaking events and accidents, but no one was up to now able to establish a clear relationship, also because of lack of data. The insurance company do have a lot of data, but they do not share, so it's not so easy to give a scientific evidence of that. And finally, the throughput is just the flux. How many cars are going through a point per unit of time? So the experiment starts. I'm sorry that the production is a little bit, the movie is continuous, but since it's a bit heavy, it's going like, okay, now it's accelerating a bit. So we start the experiment, and after some time, we show the appearance of waves, exactly as the Japanese experiment did. So you will see again, I'm sorry, it's a bit sketchy, but if you look at the graph down, you will see that there is a clear appearance of waves, and you can notice that by this oscillation in speeds. So here it's time, and we represent the speed of the autonomous vehicle. Again, when it's red, it's human-driven, and in grays are all the speeds of all the other vehicles. So you see that they start to oscillate more and more. An interesting phenomenon you see here is how you detect the waves also by this measurement. So when the waves start, you see you have a jump up of the standard deviation of the speed. You have also a jump up of the fuel consumption, because one of the main reasons fuel consumption is really that you accelerate and brake a lot. So the fuel consumption you see is increasing a lot. And the braking events are also increasing dramatically. You go from 1.66 events to 8.58. What is interesting is that the throughput really doesn't change much. So how many cars pass through a given point? This is more or less well known to be almost an invariant. So whatever you do in traffic, most of the time you are not going to improve so much how much cars are going through a point. But you could still act on different things, like the travel time, the fuel consumption, and the braking events. So let me show you what happens now. Now autonomy is started, and essentially we tried a battery of different control algorithms. Clearly, when you try to apply to a real situation, there are a lot of technology and software constraints that you have to go through. So you design a control, and then you have to modify, I don't know, 100 times before being able really to put over the car. But the interesting point is that essentially what the car tries to do is to avoid oscillating. So tries to drive at a speed that is essentially constant. But obviously you have the constraint because you have cars in front of you, so you cannot always drive at the speed that you want. What happens anyway, autonomy is working pretty well. So you see that here immediately when the car initially oscillates, but then is able to tame somehow these oscillations. And these are different parts of the experiments corresponding to, I'm sorry, it stopped. Okay, corresponding a different target velocity we were trying to reproduce. So let me run a little bit more. I will probably go here. Okay, this is the time of the experiment where we tried the different autonomy speed. So you see here we were targeting the 6.5 meters per second, and we were able to tame the oscillations. Then we raised to 7, to 750. Somehow 8 meters per second was a kind of upper boundary. When we targeted that speed, then we started to have oscillations up and down. So somehow some waves were reappearing, and then here we were readjusting to 750, and we were going back, you see, to tame in some waves. But let me show you the number upstairs that are very interesting. So you see here again, this was the velocity standard deviation when we started the experiment. This was the jump up when the wave started. And this is the result that we achieved with autonomy. You see that we were able to go down, and not only go much down with respect to the waves, but we were improving even the situation when the traffic was pretty regular without the waves. And you see that we were able to push down to 0.64, that is around 1/3 of our initial and 1/5 of the situation where waves were there. Fuel consumption is also impressive because we started at this level, we went up, and when we start autonomy, we can push down to 14.1. So you see it's something like a 40% decrease in fuel consumption with respect to the situation of waves. So even if you are not going to improve a lot of the throughput, you are going to be able to spare something like 40% in terms of fuel. And the braking events is even more dramatic. You see we had around 1.5 braking events when the waves were not present. Then we jumped up at 8.5 braking events. And then when autonomy started, we were able really to dramatically reduce that. In our best situation, that was autonomy at 7.5, we had that the braking events almost disappeared. So increasing a lot also safety. As I mentioned before, you see the throughput is also slightly increasing, but this is not really the quantity that you dramatically change when you control these waves. It's really the fuel consumption and the braking events what you are mostly acting on. So let me show just the end of the experiment. At the end of the experiment is, at a certain point, we switched off the autonomous car, so it goes back to human driving, and as soon as we do that, the waves just start to reappear again. So the waves were appearing naturally, were controlled by this autonomous driving, and then they were just reappearing as soon as we stop our autonomous driving. Yeah, it stops, but it should continue, and it should show a little bit more of oscillation here. Let me see if I'm able to show that. Yes, here you see at the end more oscillation will appear, and that's it. This was the end of the experiment. Again, when the oscillations appeared again, all the numbers were going up in terms of braking events, fuel consumption, and so on and so forth. So now this was a Kleinian experiment that was conducted in a very special setting. We chose exactly the same setting of the Japanese experiment because that is very, very famous in the community of traffic and transportation engineers. But obviously it has a lot of limitations. The limitations comes, for instance, from the fact that we are just on a single lane road. And so it's really a big problem addressing the situation of multi-lane. And the main problem is the following. You see, our autonomous driving was essentially the idea of driving at some constant speed and was creating some headway. When you go to multiple lane and you create some headway, you will have some cars that will just jump into the space created by the autonomous one. Mathematically, it also creates a lot of differences because in the approach we used with Massimo, we were also designing models in which there are essentially adapted to one lane. So you can represent this one lane traffic. If you want to represent the multi-lane traffic, you're going to need to have a mixed system in which you represent, for instance, densities for each lane, and then you will have source terms that will represent the lane changing, moving from one side to the other. And what we are trying to address now is exactly both mathematically, the idea of using a multi-lane traffic. So this will be either conservation laws or mean field type equations of Poisson, but when you have one per lane and you have terms that influence one the other, this is the interesting mathematical part. The interesting application one is that we got another NSF grant and we are trying to apply this to a stretch of highway in California. Obviously, as you can imagine, this was a very controlled setting where we kind of minimized the risks. But when you need to move to a situation like a true highway, well, beside all the permissions, we are working at the idea that we will start initially to make experiment in the sense of connected vehicles. So in the sense of having human drivers that follow instructions. And then we will pass at the end of the project to the idea of using real autonomous cars. Again, with this will be cars where there are human drivers, and then there is autonomy will enter the picture. It's interesting to notice that there are already some forms of assisted driving, at least in US, but I think in Europe the situation is more or less the same. A lot of cars now mount what is called the autonomous cruise control. So if you go to the highway, you set a speed, and the car will try to match that speed. But most of the cars now have also a radar that measure the headway ahead, and so they adjust their speed also depending on the car in front of you. So usually if you have the usual cruise control, you set the speed, but if you are going too fast, there is a car in front of you, you need obviously to brake and to disengage the control. In these new modern cars, you have this radar, and so this will be automatic. They will measure the distance, and when it gets too close, they will slow down. And you don't have to do anything. So essentially, you can drive over a stretch of highway for many, many miles or kilometers without touching any command of the car. Well, you may need to steer, obviously, if it's not a straight stretch of road. But these autonomous cruise control are there in the commercial cars, and there are many of them. So that is the good news. There are true possibilities nowadays to do this type of control. The bad news is that we run a second battery of experiments I'm not able to show now. These were back in 2016. We ran this summer testing the autonomous cruise control to see if they were able to do good results like our controls. That is, dissipate these stop-and-go waves. I don't have the final results yet, but the bad news is that no one of the autonomous cruise control we tested, and we tested from many different brands, many different models, no one of them do have this type of stabilizing effect. On the contrary, most of them are just wave amplifiers. So we had the experiment where we replaced our control by the commercial controls, and the result is that the waves amplifies. But still, for instance, one car producer was able to get a good message out of it. So they repeated our experiment we did in Arizona in a very large setting, and they showed that, obviously they didn't measure the fact that their control amplify waves, but they measured the fact that their control amplify waves less than humans do. So essentially, the game is the following. Humans do terrible. Well, terrible not because they are bad drivers, but just because it's a global phenomenon. And our control is incredibly good, but not commercially available. And what is commercially available currently amplify waves, but is not as bad as the human driving. So it's somehow in between. So the hope is that now moving this type of experiment to highway level, we will be able finally to influence also the car manufacturer towards moving this type of control that could give enormous benefit. You see, 40% of decrease in fuel consumption implies a lot of improvement also in terms of pollution, so environmental impact. So that's the hope and the idea. I have the last slide, so I should be on time. Obviously, this type of work, especially the applied one, so I started with the very first proposal that is a single-man paper, all the way down here where you have an experiment that involved around 60 people to run it. And so there is mathematics, engineering in between. All this work wouldn't be absolutely possible without a large set of very nice and great collaborators. So my last slide is devoted to them. I grouped them by area where they work. Today I really talked mainly about crowd dynamics and vehicular traffic, but many of them worked on many different areas. You see here Massimo, Giulia is somewhere here. Now, here we go. Here is Magali. So you see a few people here. So you see many of them are smiling, so it looks like they are having good time working on this type of math and applications. So similarly, I hope you had some good time following the seminar. Thank you very much.
So thank you very much for your talk, which is open for questions, discussion.
So is there anything from your theory or from kind of the experiments that you can say about the number m of controlled cars? Yeah, so that's
fantastic question. So this is absolutely enormously relevant. In the literature of transportation engineering, the number of cars that you are controlling in terms of percentage is called the penetration rate. So the penetration rate, in the experiment, we used 1 car out of 21. So we were using around 5% of penetration rate, 1 car out of 20. And that is exactly the rate that is already known to be sufficient to measure traffic. So around 2008, with the similar group, we ran experiment in the Berkeley area, the San Francisco Bay Area, called the Century Experiment, and then Mobile Millennium Project is called. That project, mostly based at Berkeley, showed that with 5% penetration rate, you can measure traffic. That is, you can really know what is the traffic situation on your network. So we were using the same type of penetration rate, and this experiment essentially shows that at 5% penetration level, 1 car over 20, you can tame waves. Now, a big jump ahead, as explained, will be when we move, as we are doing, to multi-lane traffic, and the number will be bigger, probably will be bigger. So we will need, we expect to need definitely a higher number, a higher penetration rate to be able to control traffic in the multi-lane setting. The autonomous cruise control are present in the market even a much higher rate. The presence of fully autonomous car is really much more a question mark. But the idea would be that if we have a more advanced autonomous cruise control paired with some communication rate among cars, we should be able to have those type of rates also at real traffic level.
Okay, thank you. Second question?
I actually had the same question, but from the theoretical point of view.
Mm-hmm.
Does this mean that m must grow as a fraction of n? In your limit theorems?
Well, so Massimo is shaking the head. So theoretically, no. So we keep fixed m and we send n to infinity,
okay,
and you obtain the limit. And so all the theoretical work there, you fix m and you pass in the limit only in n. Okay. Yeah. But obviously, you may imagine different type of limits, and I think it would be interesting to see if when you have a fraction of the population. Yeah, you want to comment on that?
Yeah, I think that you have to think also the influence that a single particle have. So the number it might not be the most important thing. What is very important is whether somehow the range of mass that you are able to control become more relevant somehow with the n going to infinity. And what is important is that at the n going to infinity, the mass that you need to control is not everybody, but just a portion, right?
So there are some results that we gave, for instance, Mathen with his group, our group gave different results where we put conditions, for instance, either on the size of the set you control or the size of the population you control, because you could fix a set of a given Lebesgue measure, or you put a constraint on the mass that you control of the measure that you are controlling. Okay, those type of constraints are the typical ones that are used at theoretical level.
Further questions? This is not
so. I'm not selling yet the control. So nice.
Okay. So, thank you very much for the talk. We now have the coffee break till the 15 past 11. So, welcome back to the second part of this morning session. We will have 2 talks before the lunch break. And the first talk will be given by Martin Huesmann, and his talk title is on stretch Brownian motions and friends.
Yes. Okay, so thank you very much for this nice introduction, and also special thanks to the organizers and also those who did not organize for this very nice meeting. So I'm going to talk about something related to martingale optimal transport, so something that Nassif talked about on Monday. And the interest in this topic is, well, I say, from my point of view, manifold. So on the one hand, there's some motivation coming from mathematical finance. I will talk about this at the very end a bit. But I think my own main motivation on this is really about understanding martingales and understanding structure of martingales, because martingales are kind of the main building block for modern stochastic analysis. And if you want to construct stochastic processes, essentially what you need to do is to, well, one part of it is understanding martingales. So very rough goal for today is, well, if you've given two probability measures, mu and nu, I want to construct a continuous time martingale between these two measures. And I want to construct a certain natural martingale between these measures. So now this audience is quite diverse, so let me give you a very quick reminder on martingales. So I don't expect any of you to be an expert on martingales, so also particularly if you have any questions in between, just stop and ask. So the very basic object is a kind of a discrete time martingale. So it's really just a one-step process in time. And it's a martingale if, well, with respect to just f0, which is a sigma algebra, if the first random variable is f0 measurable, and if the projection of m1 with respect to f0, so the conditional expectation with respect to f0 is m0. Or if you prefer analytical terms, if you take a disintegration of the joint distribution with respect to the first margin, and then if you take the mean of this, this is precisely should give you m0. So this is kind of the analytical version of this expression here. So now this is a discrete time martingale. What I'm interested in are really continuous time martingales. So you have a full process here, so with a continuous in time. And this is a martingale if for all times s and t, the process ms mt is a discrete time martingale. So for all s and t, the conditional expectation of mt with respect to fs is ms, or if you like the L2 projection on the space of fs measurable functions, this is ms almost surely. Okay, so these are martingales, and now I want to, so given two measures, I want to find a kind of natural martingale between these two measures. And well, very natural martingale is, for me at least, it's Brownian motion. So I do not want to have just some martingale, I want to have a natural martingale, and what I mean here is I really want to have a process starting in mu, ending in nu, and looking like Brownian motion somewhat as close as possible. Okay, so now this is a little bit too good to be true. So you need to have some assumptions here, because this martingales always have a direction in time, and as Nassif explained you on Monday, if you take the conditional version of Jensen's inequality, if you take the integral of phi with respect to the first marginal, then this is the same as the expectation of m0, and if you now take the conditional version of Jensen's inequality, you get an inequality here, which gives you kind of an increase with respect to any convex function. So necessary condition such that there is a martingale is that these measures are increasing in convex order, which I denote by this sign here, which really means that this inequality is true for any convex function. And now Strassen says, okay, this is not just as necessary, but also sufficient condition that there is a martingale. So really what I'm after is I need to have this assumption here, and now I'm looking for processes which connect these two marginals and which look very much like a Brownian motion. Okay, now this is a very vague goal, so let me be very explicit now and give you one concrete example of a martingale in a very special situation, which is really the martingale that I'm after. And now this is a following situation. I take as a first marginal, I just take a Dirac in 0, and I take just an arbitrary measure which is in convex order to this Dirac, which just means that nu has mean 0. Okay, so now I can construct a certain martingale, which is sometimes in certain communities known as the best martingale. What you do, you start with a Brownian motion. So remember, I want to be as close as possible to Brownian motion. So you start with this Brownian motion, starting in a single point. So at time 1, Brownian motion is a Gaussian distribution. Now this is a very nice distribution. So you can just take an increasing map, f, so map for just a gradient of a convex function, push this Gaussian to nu. So this gives you, this is what this map is doing here. And now you define a martingale by just taking the conditional expectation of f of a Brownian motion at time 1 with respect to a Brownian filtration ft. So essentially, by definition, this is a martingale. And now the Brownian filtration is very nice because the Brownian motion is a Markov process. So this filtration here is essentially this conditional expectation is just conditioned on the value of the Brownian motion at time t. And now this is even nicer because now you know that this is a measurable function of the value of the Brownian motion at time t. Well, if you don't like this stuff, you can think of this in analytical terms. So ft is just f, which is just the heat semi-root applied for time 1 minus t to f. So what this means is you look at where you currently are at time t, and then you average out the kind of remaining motion of the Brownian motion up to time 1. Okay, so now if you look at the marginals of this process here, which I kind of sketched down here, well, the kind of marginal at time 1 is just by construction, m1 is equal to f of b1, and f was chosen in such a way that the distribution of m1 is precisely nu. Okay, so now the distribution of m0, because the Brownian motion starts in a single Dirac, this will be m0 will also be a single Dirac, and this will just be the expectation of f of b1. The expectation of f of b1 is nu, because nu is in convex order with 0. This will be just 0. So this is precisely our measure mu that we started with. And now what we did here is we kind of deformed the space, or we stretched the space with kind of the scaling function f, so the gradient of the convex function, to come up with a new martingale, which really moves like a Brownian motion, but in this deformed space. Okay, so now this is really the martingale that I want to understand, and the question is, can I do this for general measures mu? And well, if I want to have a chance of getting a general starting measure here, I need to be more clever than just starting with a Dirac, because if I start with a Dirac here, the only chance is that I end up with a Dirac down here. So the most obvious idea is to not start with a Dirac, but to start with a general measure alpha. Okay, now if I start a Brownian motion with a general measure alpha, I end up at time 1 not with a distribution of a standard Gaussian, but just a convolution of alpha with a standard Gaussian. Okay, this is still a very nice measure. So I can always find, for each alpha, I can find a map f pushing, or a gradient, even a gradient of a convex function, pushing this measure to my target measure nu. Now I can do the same construction as before. I just take f of b1, takes a conditional expectation, respect to ft. This is my martingale mt. This is still a nice function of bt. But now the problem here is that b0 is distributed according to alpha. If I now look at the marginals of this process here, then these marginals here depend so I mean, the marginal at time 1 is precisely nu, but the marginal at time 0 is this map f0 pushing alpha. So it's, at least for us, it was completely non-obvious whether for each mu I find an alpha such that this f0, and now recall that f depends on alpha, because f pushes alpha convoluted with gamma to nu, whether for each mu I can find an alpha such that f0 of alpha, the push forward of alpha via this map f0, is my initial measure mu. So okay, so this is essentially, if you don't like this very vague question from the beginning, the kind of question I want to ask in this talk, I want to answer in this talk, is whether I can find such an alpha such that for each initial measure mu and target measure nu, I can find an alpha and do exactly this construction. So this is a very explicit question, and because what I essentially do here is I take a martingale, well, I take the Brownian motion, I deform space with or I stretch my space, if I want, with this map f. We call this process, what we have here, we call stretched Brownian motion. Okay, so there are certainly some examples of stretched Brownian motion, and the most easy example is the Brownian motion itself, because, I mean, sure, this is a Brownian motion, you don't need to do anything. But there's also a less trivial example, which is geometric Brownian motion. You can convince yourself that this is also stretched Brownian motion. It's e to the Brownian motion minus compensator. Okay, so the question is, how can we actually do this? How can we understand whether it's possible to do this? And well, in this conference, the obvious answer to this question is you should do optimal transport. And what we do is we looked at some kind of martingale, Benamou-Brenier type problems. So we looked at a kind of whole family of problems, and which are inspired by the Benamou-Brenier formulation of the transport problem. And let me call this, we call this in kind of very probabilistic terms, which are maybe a bit unusual to most of you, because I'm really after a process. I'm not so much after the evolution of measures, I really want to construct the process here. So this is, in probabilistic terms, the Benamou-Brenier formulation. And now the question is, what is a good replacement for this, for the martingale setup? And the main problem is, of course, that here you have a speed of a particle, and martingales, especially those who are very close to Brownian motion, they are not differentiable. I mean, they are just Hölder continuous. So you don't have something like a speed, but if you also think that this is that martingales are Hölder continuous, and a good kind of measurement is you should look at the quadratic scale of the martingale. And I'm not sure whether all of you know this. So if you look at the quadratic scale of a martingale, then what you do is you look at the square of the martingale. But now the square of a martingale is not a martingale anymore, it's a submartingale, so you need to compensate this to become a martingale again. So you need to subtract something which is called, so if you want to make this a martingale again, you need to subtract an increasing process, which is called the quadratic variation. And it's often denoted with these brackets. And now this is a martingale again. So now what this is really kind of the mean, or the kind of the quadratic movement of the martingale. So this is the kind of scaling in which the martingale moves. So now what we do here is now, so jointly with Dario, what we looked at, we replaced the speed here with the speed of the quadratic variation. So this here is the quadratic variation, and the dot here is supposed to be the speed. So what we assume is that we only look at martingales which are absolutely continuous with respect to the Lebesgue measure. And now this is the object that we think of as the speed of the martingale. So this is the speed, so how fast the martingale is moving. So except of, now this is really can just, okay, now there's not a square but a general C, but otherwise it's really just the same formulation. Okay, so if you do not like this stochastic version so much, there's also another formulation, which is via Fokker-Planck equations, which is then probably much closer to what most of you are used to. But here, I mean, the continuity equation is now just replaced by this Fokker-Planck equation. And now here I want to stress that here I'm only looking at dimension 1. Yeah, we can do all of this in higher dimensions. So here is also read dimension 1. But I prefer to work in dimension 1, or I just write here everything in dimension 1 because dimension 1 is much, much, much nicer. Everything is cleaner. Here, if you do this in higher dimensions, here there's a trace and a Hessian appearing. So the formulas become more complicated, and in dimension 1 we can say much more. Most of this, what I'm telling you, is essentially true in higher dimensions as well, but you need to assume just much, much more. And every now and then I just tell you what you need to change in higher dimensions, or explain you a little bit of why higher dimensions are much more complicated. Yeah? And Nassif in his talk already told you a little bit why high dimensions in martingale transport are very complicated, and it's a big open field for anyone who's, even if you don't like stochastics, you just like convex analysis, there are very many interesting open questions. Okay, so these are the two formulations. And now I want to stress once more, and this is very similar to what Giovanni said yesterday. This here is really a complexity reduction towards compared to this problem, because here you really talk about processes which take into account correlations between different time instances. And here you really only look at evolution of measures. But nevertheless, if you assume something, so if you assume that this is convex, so if the cost function is convex, then at least the values of these two problems, this is a good start, these values are really the same. And I mean, to give you an idea of the proof, well, one direction is really the superposition principle by Dario for the martingale problem. So any solution to this to the Fokker-Planck equation here can be lifted to a solution to the Martingale problem. So you can really construct a process such that the speed of the quadratic variation is precisely the diffusion coefficient here. And now for the other direction, the problem here is that this quadratic variation here is allowed to depend on the whole evolution of the path. Yeah? So there's no Markovianity here. Yeah? Whereas this diffusion constant, or this diffusion coefficient here, this is kind of only depends on the state where you currently are. Yeah? And this is where the convexity kicks in. So to show this equality here, you just take in admissible martingale, and then you do a projection argument, or if you prefer stochastic words, you do a conditioning on the current value. And then the convexity tells you, okay, if you do this, you construct a martingale which is even better for this problem, because then the conditional Jensen kicks in. And this tells you that you can restrict to martingales which are really in more or less one-to-one correspondence here. And this is, but it's really just more or less. And come back at the end of the next slide, I come back to why I say it's more or less. Okay, but this is a start, and this is really a kind of a good formulation for this problem, because now we can employ standard techniques and essentially look at the proofs of this duality result. And okay, so then you can just adapt this duality result, where you now as a kind of an equation for the dual potentials, you get this Hamilton-Jacobi-Bellman equation here. And now this C star is a convex conjugate of C, and now here the well, 1/2 of the Laplacian of phi t pops in. Okay, now this is quite nice, and the first thing that you do as soon as you have duality, this allows you to get some kind of optimality condition. So now there's a sufficient condition for optimality, and this tells you, well, okay, if you have a solution to this equation, which is sufficiently nice, and I say it's smooth, so it's really a nice solution to this equation. Now you can construct out of this solution, you can construct a diffusion coefficient A via this this formula. So you really need so you plug in the Laplacian of phi t, and it takes a gradient of C star. This gives you the right diffusion coefficient. And now you plug this into the Fokker-Planck equation, you solve the Fokker-Planck equation, and then the solution will be optimal between its marginals between each time S and T. And this is kind of automatic just because of this duality. Okay, so now why is this useful? Because this allows you to actually construct optimizers is the first step. And the way how do you do this? Well, you would need to solve this equation. But now this becomes very nice if you do a change of variables. And now there's a very nice change of variables, which unfortunately only works nicely in dimension 1. Because now if you write, I mean, you see here, this is kind of the Laplacian of phi is a real variable that you're interested in. So you write u as 1/2 of the Laplacian of phi. Now if you plug this into this equation and you just take the Laplacian on both sides, so then on the right-hand side, if you take 1/2 of the Laplacian of phi, then you have u. So this is the time derivative of u. Mi is equal to minus, well, 1/2 of the Laplacian of C star of u. But this is precisely the porous medium equation. So if you make a change of variables of this type here, then what you end up with is this equation here. Time derivative of u is minus 2 times Laplacian of C star of u. So this is precisely the porous medium equation. So now you can rely on the theory of porous medium equations to construct solution to this equation, and to come up with optimizers for really concrete examples. Now this is very nice, but it's unfortunately a little bit. Well, if I tell you like this, it sounds too nice, because there's a kind of little problem here, because this is a C star. And the C is not, I mean, C of A is equal to A to the power P, but only if A is positive. Diffusion coefficients are positive here. So, but it's infinity if it's negative. And this infinity causes a positive part appearing in the C star. So the convex conjugate is a positive, so if this is to the power P, this is a positive part to the power Q. Now, and the positive part is kind of makes this C star here slightly irregular, so yet you cannot directly use all the nice theory in the book of Vasquez, for example, on porous medium equations. It just doesn't fit directly to this. So why would we want to fit this? Because in principle, we're not really, well, we want to have information about the processes. But now to come back from the evolution here to the processes, the way to go back is via the martingale problem. So now, for example, if you're interested in asking kind of uniqueness to our problems, convexity allows us to directly get uniqueness on the level of curves. But if you want to get uniqueness on for the level of processes, so uniqueness in law, this is a question on uniqueness of solutions to the martingale problem. And now questions on uniqueness to martingale problems are essentially linked to regularity issues of the diffusion coefficient of A. So the question is, how regular are the optimal A's here? Right? So how regular are the optimal solutions that we get via this procedure, say? And now in some special situations, we can kind of resolve this, and it gives us precisely, and unfortunately only dimension 1, it gives us precisely Hölder-Lipschitz regularity for A. And this is exactly what we need in dimension 1 to get uniqueness for the martingale problem. But this is really borderline, and we need assumptions, and we have not yet, say, fully resolved this. It might also be a lack of knowledge on porous medium equations, but there's a little problem here. And we have no idea in higher dimensions. But in higher dimensions, what you get here the Hessian, and I think this is a different story. And this is also the point why we are not working with viscosity solutions, because they, at least from what we know about viscosity solutions, they would not help us to get regularity on A here. At least not the direct theory that we would have. So if any of you has a good idea, we're happy to hear this. Okay, so this gives us now a full family of kind of possible ways of interpolating or finding martingales between these two measures. And now let's have a look at our example again. Let's look at the stretch Brownian motion. And now this is very explicit here. We constructed this from Brownian motion just by a kind of a change of variables in some sense. Now we can just use this very explicit formula, plug this, just check, essentially calculate the diffusion coefficient and check whether this diffusion coefficient might, by some chance, just solve some nice PDE that we saw on the previous slide. Now, if you do this, you see that this solves this PDE, but not for p bigger than 1, but for p exactly equal to 1/2. So this, what you need to do now is you need to consider this optimization problem, but now corresponding to the square root of A with a minus. So this is now not convex, but concave. So what you need to do is you should not look at the minimization, but as a maximization problem. Okay, so now what is this problem that we're looking at? Now I've slightly rewritten this problem, now directly back in probabilistic terms. Now here it should be A to the 1/2. Now in probabilistic terms you look at martingales, and now there are kind of two things. There's a sigma appearing here. Previously there was an A, and now there's a martingale here, and it's a Brownian martingale. Okay, why is let's first look why there's this Brownian martingale. So this martingale, which can be just written as a Brownian integral, and the reason is precisely here. What we assume here is that the quadratic variation is absolutely continuous with respect to Lebesgue measure. And now what kind of abstract stochastic analysis tells you is that martingales of this form are essentially Brownian martingales. So if you have this representation of the quadratic variation, then the martingale is a Brownian martingale, so you can restrict to martingales of this form. And now if you have this martingale, then the quadratic variation of this martingale is a sigma squared. So now the square root of sigma squared is sigma. So what you need to do is you just take the supremum over sigma here. So now if you look in higher dimensions, what you have here is a supremum instead of sigma, you have a trace of sigma. So this is a matrix. So now the first question, okay, is this a kind of a well-defined optimization problem, or is this, or are there, can you impose certain conditions that this is finite? And now there's some stochastic analysis here. So what this here is kind of the cross variation between the martingale and the Brownian motion. So now if you want to do with this, you can also just take a Cauchy-Schwarz inequality. And what you see, you can bound this by the second moment. And the second moments here are just information that you have on the marginals. So as soon as you have second moment on the marginals, you know that it's finite. Okay. So this is kind of a nice optimization problem where you have some control as soon as you have some moments. Okay, so now there's a theorem jointly with a gang from Vienna, which says, okay, here to this problem there's a unique solution, and this solution is unique in law. And the second part is that any stretch Brownian motion is really an optimizer to this problem. Okay, so now the question is, well, if this really is any stretch Brownian motion is an optimizer, are there also optimizers which are not stretch Brownian motions? And unfortunately, not every optimizer is actually a stretch Brownian motion. And now the reason for this is kind of, well, was already stated somewhat in Nassif's talk. And it's a very peculiar and I think very interesting thing from martingale optimal transport. So opposed to transport, in martingale optimal transport, there are certain regions which do not communicate with each other. So there's an additional freedom and there's additional complication. And so the reason why not every optimizer is a stretch Brownian motion is precisely that there are certain barriers for your transport problem. And so I think the first time that this was understood was in the paper by Nicola and Matthias. And I very much like this argument because it's very short and it shows you a little bit why martingale optimal transport is one of the special features of martingale optimal transport. And it also shows why it's much more complicated in higher dimension. So I would like to explain this just on this slide. So it really just takes a few lines. So remember that the necessary and sufficient condition that there is a martingale is that these measures are in convex order. Now in one dimension, and this is kind of the problem, that only in one dimension you can check convex order by looking at the potential functions, the Newtonian potential functions, which are just the integral of the absolute value of x minus z. So now checking whether mu and nu are in convex order is the same as checking whether these potential functions are ordered for each point z. And the reason is that these essentially span all convex functions in dimension 1. Okay, so now let's assume, let's take these two potential functions and assume there is a point where these potential functions actually agree. You do not have the inequality, but you really have an equality between these two functions at this point. Now take any martingale coupling pi, it really doesn't matter which one, take any martingale coupling between them and you know it exists because they're in convex order. And now you take this potential and now because you know this is a martingale coupling, you can rewrite x as a mean of the disintegration of pi with respect to the first marginal. So pi x is a disintegration of pi with respect to mu. Now you know because it's a martingale coupling, the mean of this one is precisely x. Now z is independent of this integral. This is a probability measure, so you can just put this z under the integral as well. Okay, now what you do is you apply Jensen's inequality, so you get an inequality here. Now this integral here, because it's a coupling between mu and nu, now there's no x anymore here, you can just integrate this out to get the measure nu. And now this here, what you get here, is precisely the definition of the potential function for nu. Right? But now by assumptions, these two potential functions agree. So the left-hand side is equal to the right-hand side. So this means that you have equality everywhere. But this means that you have equality. So now the step in the inequality here was a Jensen inequality. But you precisely know what are the equality cases for Jensen. And these are the cases when you have an affine function. So this means that under this measure pi that you have here, under this coupling, for this martingale here, this function that you're integrating looks affine at the point z. So, but this means now this function here, how does it look like? It's this function here, right? So if this looks affine, this means that if you start on the left of z, you do not see this kink, which means you do not see anything that happens afterwards. If you start to the right of this, you do not see anything that happens to the left of it. So this means that under the measure pi, you know that if you start with your martingale on the left of z, you certainly end up to the left of z. You cannot cross this part. And in the same spirit, if you start to the right of z, you cannot end up to the left of z. So this set here has full measure. And this argument here did not use any special properties of pi, so this is true as soon as you have, I mean, this is true for any martingale coupling. Particularly if you find one martingale coupling where you have this property here, you get equality. This is already true for every martingale coupling. So this is a very interesting feature of martingale transport. And it also gives you a glimpse on why this is more complicated in higher dimensions, because in higher dimensions, convex functions are much more complicated. And there is nothing like such a nice potential which allows you to translate the information of convex order in such an easy way. And this, then you really need to work very hard, use very, well, the proofs or the results that we have so far use very heavy convex analysis machinery to get similar results in higher dimensions. So now, why is this result very useful? Because it now tells you precisely what you need to do to understand this martingale transport. You have no hope, well, if you have this z here with this property, you have no hope to transport over this z, but these functions here are very nice. So you only need to check, you take these two functions, you check all the points where they agree, these are the barriers, so but this decomposes your space into open intervals, and on each of these intervals you can do the transport. But you also know that these different intervals, disjoint intervals, do not communicate with each other. So this gives you automatically, unfortunately only dimension 1, a unique decomposition of your measures mu and nu and of each martingale coupling. And so-called irreducible components. These measures are called, or these open intervals are called irreducible components. And now dimension 1 is so special because the boundary of open intervals are just single points, and there's not much choice what you can do with a single point if the single point is not allowed to move either left or right. So then you can only stay where you are. So this really gives you very nice and unique decomposition of your coupling. Whereas in higher dimensions, the boundaries of convex sets are much more complicated. And then you're allowed still to move within the boundary, and one can still control this in 2 dimensions, but as soon as you go to higher dimensions, we have not yet a good understanding of this. Okay, so this is why this failed. Why not every optimizer is a stretch boundary motion, but the next best guess is that on each irreducible component, each optimizer is a stretch boundary motion, and this is in fact true. Now what you can do is you can just decompose your problem into irreducible components, and on each irreducible component you get a stretch boundary motion. Okay, so now why is this true? So let me give you an idea on the proof, and so if you want to prove classically, well, if you want to work with, if you want to find solutions to the classical Benamo-Brenier formulation, then a very powerful way, and very similar to the Schrödinger problem, as explained by Luca and by Giovanni, is to relate it to a static version of the problem. And in classical transport, at least on Rn, it's very simple. You just take the map and you take the linear interpolation between the target and the initial point. Now, this is doomed to fail in martingale transport because of this Berry center condition. If you take in disintegration, you need, if you start in x and you do not stay in x, then if you move upwards, then you also need to move downwards, so that because a kernel needs to have this Berry center condition. So the integral, or the mean of pi x needs to be, or the condition expectation needs to be x, right? So if you do this between time 0 and time 1, this is okay. But if you do it between time 0 and time 1/2, and then between time 1/2 and time 1, you really get a diffusive nature. It's a bit like a random walk approximation to Brownian motion. So it's not really discrete martingale transport problem that ends, well, classical discrete martingale transport, but still there's a very nice problem. And this is a so-called generalized transport problem, which is the following. Now you start with your objective function that you want to maximize, and okay, now just basic stochastic analysis tells you this is precisely the same as it's a difference of m1 b1 minus m0 times b0. Now m is a martingale, so you can rewrite this as m1 times b1, which is the first term, minus m1 times b0, because b0 is f0 measurable, and m0 is just m is a martingale. So now you condition on m0, this doesn't change anything, and now you take the law of this of this random variable here. You call this q. So qx is the law of the joint law of m1 and the increment of the Brownian motion, condition on m0 being x. Now the distribution of m0 was mu. So what you end up here is precisely this quantity here, right? So now the marginals of this one are, well, on the one hand, this is just the increment of a Brownian motion, so this is just a standard Gaussian. And on the other hand, this is a law of m1 conditioned that my martingale started in x. So this is really kind of the kernel between time 0 and time 1 of my martingale. Now this here is a function essentially of my kernel here. So if we can kind of connect to this problem here, a quite complicated looking so-called generalized transport problem. Why is it generalized? Because here the kernel appears and not just points. So this was introduced by Gosselin, Samson, Roberto, and Titali, I think 2 years ago. And now what you do here is you just take this functional here, which is precisely this one. You optimize inside via each possible coupling that you can come up with between these two marginals here. So this makes this quantity inside as big as possible. But you also have an optimization problem, optimization outside, where you optimize over all kernels pi x, or if you want all couplings, because if you integrate this kernel with mu, what you want to end up with is your target measure nu, and you have this martingale constraint that the mean of pi x is equal to x. Now this is pi, so this pi d mu is really just a martingale coupling between mu and nu. And the mu x is a disintegrated version of this pi. And now this is what I call the generalized problem. And now because you can associate to each admissible martingale for my dynamical problem, by this procedure, you can associate well, an admissible candidate for this problem. You directly get this this value here is bigger than the martingale version, right? But now you can also go the other direction. If you have a candidate for this guy, now you precisely know what the optimizers to this problem look like, because this is just a standard L2 optimal transport problem. So for each x, you can find the gradient of a convex function, so the gradient of fx, now optimizing this quantity here. And now you just need to come up with a martingale which gives you precisely this quantity here. But now this is very easy, because you can just do exactly the same construction as I did before. You do the standard Brownian motion, where for each x you take as a map, you take the gradient of fx. And now you only need to make sure that at the beginning you start with the right measure. So you need to add a random variable with the right distribution. But now then you can define mx via exactly the same procedure as I explained to you on the second slide. And now if you do this computation, then from the last slide again, you see that you get exactly the same value here. So you can associate to each candidate here you can associate a solution which gives you essentially the same value. So these two problems are really equivalent, and they are very much equivalent in the sense that there's really a one-to-one correspondence between the solutions to the static problem and between the solutions to the dynamic problem, and they're related precisely in this fashion here. So now this is very nice because it gives you a way of constructing this. The only problem is that these maps here depend on the position that you started with. And this is what you do not want. I claim that there's one map, one measure that you start with, and not just for every x that you start with, you have a different map. Okay, now this is the second step of the proof. And now what you need to do, well, the main idea is, well, by some dynamic programming principle, you can show that the optimizer to this problem is a strong Markov process. So now if you start in two different points on an irreducible component, then they start diffusing, and at some point they will meet. But if they meet, they immediately forget from where they came from. But from this point to the final position, this is again needs to be a stretch Brownian motion. So from this point, so if you need to forget where you came from, then at least from this point onwards, you have to have the same map. But this map is already defined from time 1, because at time, say, t, this is just a heat semigroup applied to this map. So in this, okay, so this is kind of the main idea, that the maps cannot be too different, because Brownian particles meet, and then everything needs to look the same. And to make this explicit, you need really to use this this generalized transport problem and to come up with some kind of C-monotonicity for this, which was to really show that certain things which are not so good do not happen. This is in one dimension not too complicated, in higher dimensions very complicated, because convex sets are more complicated in higher dimensions. I would also like to point to so this is the article where they came up with this problem, and now there was a recent article by Gosselin and Nicola where they extended the C monotonicity to really cyclical monotonicity, and had some very nice applications, I think. Okay, so this is essentially the way how you prove this. And I think, okay, from a personal point of view, this was quite nice, because we thought quite some time about how to construct stretch Brownian motion for general starting law. But now I think this is a really interesting object is essentially this slide. So if you haven't taken anything way so far, I think this is why this is really getting interesting now. And let me first start with a quick point of view on the standard Benjamin-Brenier formulation. So previously I had this with v being 0, but now it's not so hard to see that if you pick any deterministic v inside, then the minimizer is still just a classical minimizer here. So I mean it's what did I write there? Okay, this should not be so there should not be an expectation here. Sorry. So the okay. Well, what's on the left-hand side is still the. So if you look at the minimizer of this optimization problem here, then what you get is precisely the minimizers that you get for the Benjamin-Brenier formulation. This particle doesn't really matter so much. Whether it's a particle with speed 0 or with constant speed doesn't matter, because if you just take the squared here, the v squared is just a constant, and if you take the x dot times v, then this x dot, if you integrate this, is just the mean. It's the difference of the mean of nu minus difference of the mean of mu, which is just data which is given to the problem. So the minimizers don't matter so much. So you can think of the minimizer here as being a certain distance, some kind of Cameron-Martin distance to a constant speed particle. So now you can do this similarly with stretched Brownian motion. So if you stretched Brownian motion is okay, so there should also not be an expectation here. Sorry for this. So this is kind of the original optimization problem here. And in a similar way, you can just smuggle in just just a difference with a constant volatility martingale. And now if you replace this, then you end up with such a formulation, or with such a formulation. And now what you see is this is very similar to the original formulation, but instead of a constant speed particle, you get a constant volatility martingale. And there's one more thing here, is that this martingale and the Brownian motion are coupled not just at time 1, but at each time t. So the way I couple the martingale with the Brownian motion is in a certain causal way that I need to reflect the filtration structure, so the information flow of the problem. So I'm not allowed to couple a certain event which happens at time t with an event that happens at time 1. So now why is this interesting? Because it tells you, well, one interpretation of this result is that stretched Brownian motion is a projection of Brownian motion on the set of martingales with a certain prescribed initial and terminal law. And now from a very applied point of view, from say finance point of view, now what are you doing here? You think, well, one interpretation is your market tells you that your stock price is tomorrow has a distribution mu, and the day after tomorrow distribution nu, and a possible model that you think is a very reasonable model, say Brownian motion. And now you want to calibrate your Brownian motion over certain parameters of your model, and in this case it's Brownian motion. You want to calibrate to the market data. And now the calibration that you can do with kind of this idea here is what you do is you just project it with a certain distance on the set of all models which satisfy this market data. And this is very similar in spirit to Marco Couturi's talk. What you do is really look at this serves as a distance which takes information flow into account. And this is kind of a way of calibrating models to market data. And I think this is, from a practical point of view, is very interesting. It's also interesting from a stochastic analysis point of view, but I will not go into detail there. And let me just, also time-wise, finish with a few remarks. So I already told you that this is kind of yields a time-consistent way of interpolating between measures. And this is also interesting for functional inequalities. So some proofs of functional inequalities can be rewritten using this interpolation in really like 4 or 5 lines. Unfortunately, we have not found any new functional inequality. In higher dimensions, you can do many of these things, but they get much more complicated. And Brownian motion is not so special about it. If your kind of favorite martingale would have been some Levy process, you can also do Levy process and do similar things, and then you end up with stretched Levy processes. And you can also think, if you remember the last slide, if you think a Levy process is a good model for something, then you can project it to and calibrate the Levy process in this way. And let me finally give you a very quick result on stochastic analysis problem, which I very much like, and I think it's not well known, so this is why I want to promote this problem. So if you have a sequence of not just 2 marginals, but you have really a continuum of marginals which are increasing in convex order, then it's known that there is, and this is already a non-trivial statement, that there is a martingale matching these marginals. But this is still true in any dimension. What is not known in any dimension is whether there's a Markov martingale matching these marginals. So as soon as you attach Markov property, you acquire Markov property, it's not known in any dimension. It's only known in dimension 1. This is very surprising. Martingales Markov processes are very fundamental objects. It's very surprising. It's not possible to answer this question at the moment. But now, essentially, if you do minimization, well, kind of discretization, and attach these stretched Brownian motions, is another way of proving this result. Unfortunately, only dimension 1 so far. And it would be currently belief or hope or conjecture or a mixture of this is that we can, with some assumption, we can do something in high dimensions. But we certainly cannot resolve this in full. So this is a surprisingly difficult open question in stochastic analysis. Okay, and then I think my time is up, so thanks for your attention.
A lecture, which is open for discussion. Other questions? Yes?
About your last remark, can you do it for sub-martingales?
Sub-martingales?
Yes.
You mean the Kellerer? Maybe.
Any further question? This is a longer answer. This is not the case. We thank the speaker once again. In the interest of time and upcoming lunch, maybe we go directly to the final talk this morning. So the last talk will be given by Karl-Theodor Sturm from Bonn University, and his title is Beyond Metric Measure Spaces with Uniform Lower Ricci Bounds.
Yeah, thank you for the introduction, and in particular thanks to the organizers for organizing this beautiful series of conferences now already since many, many years. So what I'm going to talk about today is something which is related to lower Ricci curvature bounds, which played a major role in my work in recent years, but also I guess here in this series of conferences. And I want to go in certain directions where we do not have this kind of bounds. So let me, for instance, first start a little bit with an intuitive picture. If we have lower bound of a Ricci curvature, and if we look on, so we have a space X and a subset Y, then what we could try to study are gradient estimates. So we all know that one of the consequences of this Ricci curvature bound is such a gradient estimate of a form gradient of a heat semigroup is bounded uniformly by the heat semigroup of a gradient. And we know that this is true for a metric measure space satisfying this curvature dimension condition with K. And this also is preserved if we pass from X to a convex subset of X, and if instead of a heat semigroup we use the heat semigroup with Neumann boundary conditions. This is one of the very easy and naive applications. But now what happens if we study with a non-convex set? In this case, if we restrict it with a Neumann, we know that this is not true. So the heat semigroup can satisfy such a condition if and only if a domain is convex. If it's not convex, it cannot be true. So what I want to derive today is a precise formula for the gradient of a heat semigroup for domains which are not convex, as well as an improved formula for the heat semigroup if we have a convex domain. So one of the results is that even in this case, the heat semigroup will be better than this one. It will also see the positive curvature of a boundary, if a boundary is really curved. And to summarize very briefly, the main results will be as follows. We will go through this then step by step, and it requires quite a number of new results and transformations. We have if we have a RCD space, and now anyway the proof will require that we work with variable curvature bounds, so we can start from the very beginning with a variable Ricci curvature bound. We will introduce a notion of curvature bounds for the boundary. So this is one of the new concepts entering this game here. It will be positive in the case of a convex set or non-negative, and it will be negative at these parts of a boundary. We will give a meaning which is a little bit different from the standard meaning of the surface measure of a boundary, and then we prove that the restricted space has this curvature bound coming from the ambient space. It's the variable function times the volume measure, plus a singular contribution which comes from the boundary. So this is the volume measure or the surface measure of a boundary, and this is the curvature of a boundary. So in any case, this is a measure which is singular with respect to M. If we have a convex set, this is a non-negative measure, so we simply can ignore it if we want to make a weak estimate. If a set is non-convex, this has a negative part, so it can't be ignored. And this is the reason why this kind of estimate cannot be true. And if we have this kind of estimate in the sense of a Piccoli or Bochner inequality, then by argumentation which is not too complicated, we end up with a gradient estimate. Here you see the contribution of curvature inside. This is just integrating the curvature bound along Brownian paths. And then there is this new contribution where you integrate up the curvature of a boundary against the so-called local time of a boundary. For Riemannian manifolds, all this is not new. So the fifth term had been identified by Elton Shu in his PhD thesis some 30 years ago. Thalmeier and Wang have improved all these kind of results in the case of smooth Riemannian manifolds to obtain exactly this kind of estimate. And Bangxia and Wang just last year has in the Riemannian setting also derived such a Piccoli formula where the curvature of a boundary shows up. Now let me sketch rather briefly how we try to prove our results. So we start with a metric measure space XTM, and the first step is a so-called convexification. So we will choose a transformation of a space X which makes this set to be convex within X. So we start with X with a metric and a measure, and now we change the metric in order and the measure in order that in this metric space, or with respect to this new metric, this set Y is a convex set. This is already an idea which I developed with Jana Lear, but now it's an improved result which takes into account variable curvature bound and which also takes into account a transformation. If a set is convex, it will reduce the convexity to be minimal convex. So even if we have a convex set, this transformation will be in force. This is the first transformation. To apply this, we have to work in the world of Piccoli conditions or Bochner inequalities. So first of all, we have to change from the Lagrangian world to the Eulerian world. So we need a result which helps us to transform curvature bounds from one world to the other one. If we start with a constant, this is no problem. This is then the result of Ambrosio, Gigli, Savaré, or my work with Kowada and Erba. This time change works in the world of Piccoli formula. So this time change formula now is an improved result of Bangxia and mine. Now we have to go back to the Lagrangian world, because only in the Lagrangian world we know that restriction to convex set preserves the curvature bounds. This is still an ugly thing, so you should be able to see this in the Bochner inequality. But right now we only, at least I only know this result if you are in the Lagrangian world, if you work with optimal transports. Then of course restriction to convex set does not change anything, because you do not even see that you have thrown away the rest. If you start inside, if you are in a convex set, everything is fine. You go back to the Piccoli world, and then you try. So here in this picture, this is then the Lagrangian world. You throw away the ambient space, and then you have to make the time change back to be in your original metric and measure. And there are some tricky things. So the time change which we do here is in terms of a function which will be in the domain of an operator. If we go back, so this will be the function called psi. If we go back, it will be the function minus psi. Here, on this step, we can do everything in a nice way, so we can assume that this is in the domain of an operator. But going back, this function will not be in the domain of a new operator, which is the Neumann Laplacian. So it will be crucial that this function is really singular with respect to the it will be not in the domain of operators, so the distributional valued Laplacian will have a singular part, which is exactly this curvature which pops up. So therefore here for this transformation we also have to take into account distribution valued or measure valued Ricci curvature bounds. So our time change means that we have a function psi which will be specified, and we multiply the measure by e to the 2 psi, and we multiply the distance by e to the psi, where multiplication of a distance is defined in this way. This will show up several times. So it essentially means we multiply the metric tensor, which is well defined this way. So we take the infimum over all curves connecting x and y, or Lipschitz curve if you like, and integrate this function along the curve. This is the right way to pass from one length structure to another one. And the function which we choose is essentially up to epsilon and regularization minus the curvature times the distance function from the set. So this will be our crucial object. So maybe I should write this somewhere. So psi is always essentially this lambda times v, and v is the distance function from this set y. So if we want to have a picture, okay, picture is complicated, I will make pictures later. So there are several results on which this talk is based. There is and actually 3 preprints in preparation, which all should have been finished right now, but none of them is really on the archive. There is one paper by Matthias Braun, Karl Habermann, and myself, where we prove the equivalence of Eulerian and Lagrangian curvature dimension condition with variable curvature bounds. It is a project which started already some years ago with a paper of mine and a subsequent paper of Christian Ketterer, but which at that time was not completing the circle. Then there is a recent paper of Bangshan and mine on curvature dimension under time change, and it improves on previous works of mine and of Bangshan, and now we prove this in the generality which we need. I will report on that. And then finally the content of this talk is a recent paper of mine which uses all this transformation stuff and so forth. And partly it is based, and it goes far beyond a paper by Liel and myself, where we first developed this idea of time change to attack non-convex sets. Okay, let me start with this basic equivalence of Eulerian and Lagrangian characterization of curvature bounds, which for constant curvature and without dimension is the famous result of Ambrosio, Gigli, Savaré. So we have a Lagrangian characterization in terms of this, let's say, Lott-Sturm-Villani curvature dimension condition. So it's just the K convexity of entropy. Then we have a Eulerian characterization. I don't write down now domains and test functions and so on. So it's just a weak formulation of a Bochner inequality. And then as a consequence of a Bochner inequality, you immediately end up with a gradient estimate. So 3 and 4 are very easily seen to be equivalent. Then estimate closely related with a curvature dimension condition is the transport estimate. And transport and gradient estimates are also well known related by Covada duality. Now the aim is to replace this constant by a variable function now. And actually here it's obvious what to do. As a consequence, here it's not too hard to see what to do. Here we already knew what to do. This was an open problem in closing this circle, which we started some years ago. So let me just repeat this program. So variable curvature in the Bochner inequality, of course, is no problem. Just make this k dependent on x and multiply it by test function, integrate it out. If you have it here as a function, the natural gradient estimate now is to regard this Laplacian together with this k as a Schrödinger operator, because they act on the same function. It's minus Laplace half plus k. This is the Schrödinger operator, which admits a probabilistic representation in terms of a Feynman-Katz semigroup, and this is the reason why the k pops up in this gradient estimates in this form being integrated along Brownian paths. We always have to take into account that Brownian motion actually has generated 1/2 Laplacian. Here we work with Laplacian. So sometimes I'm doing it correctly and say Brownian motion is b t/2. Sometimes I guess it's still forgotten. And then the gradient estimate, which was written here with a constant k, is then simply saying that the gradient of pt is estimated by the Schrödinger semigroup acting on the gradient. So this is the variable version, which was already known some years ago. The variable formulation of k convexity we already have seen in this conference, and this was already in my paper some years ago. You simply replace this right-hand side by integrating the variable k along the geodesics, giving weight with the one-dimensional green function on the standard interval, and integrating out this stuff. So this is not really a surprise. What we did not know for quite a long time is how to replace this quantity. And now the appropriate replacement is we put the k inside. This was clear that this should be also integrated into this term. And we simply look on this quantity where b1 and b2, this is a pair of Brownian motion, a coupled pair of Brownian motion, where this pair tries to minimize the Wasserstein distance, the L2 distance, for all t. Such a pair exists. This is just a result of optimal transport in W2. Actually, there is a nice semigroup for such a pair. It's a Markov semigroup which always produces such coupled pairs. And we plug in a coupled pair and integrate out the Ricci curvature bound. Now the Ricci curvature here in this setting, this is k bar, is a function of two variables, and it's the Ricci curvature, the mean value of a Ricci curvature between x and y. Yeah, you now work with paired Brownian motions, and you need a lower Ricci bound for pairs, and this is just the integral from x to y along the minimizing geodesic. So typically in Riemannian cases and in many applications, there's just one geodesic, when the inf is just can be dropped. There's only one curve. Along this curve, this geodesic curve, you integrate the Ricci bound. And this is now the Ricci bound for pairs, and this you plug in. If k is a constant, this of course is just 2 times the constant. It can be taken out of expectation, and then this is just the Wasserstein distance. This is just the old object. And with these objects, we have equivalence again of Eulerian and Lagrangian objects, and yeah, of course, also kn versions are important. We already started with it for constant. This is this Erber-Kowada Sturm result. For variable, Ketterer already started, but also not including this term. And there are also these PQ versions, where here we want to reduce the 2 to 1, and here we want to go to infinity. But time is limited. I won't go in this direction. An immediate consequence of this new equivalence is a nice side result, which is interesting for its own. Namely, we can improve our results on gradient flows for locally semi-convex functions. So this is just a result of independent interest. Given a metric measure space on a locally compact geodesic space, and a function k, now and a function k which measures the Ricci curvature, a function lambda which measures the convexity of V. And so V is locally lambda convex in this sense that again we have a variable lower bound for the convexity. And then for this V, there exists a unique gradient flow, and this gradient flow has this contraction property where the distance between x and y is measured by integrating the convexity bound on the way from x to y all the time along the flow. And the proof is just following the previous proof for constant curvature. We go to the weighted space, we use the curvature bound of an underlying space and the convexity bound of a potential, so we have a k plus n lambda convex functional, and then we use the contraction results just displayed, let n go to infinity, and finally this flow is a deterministic flow without any noise. So in some sense we put in first noise, we have a regularization of heat equation, and then we get the deterministic flow with this contraction result. I display this not only because it's of interest by itself, but also because it's relevant for the next result, namely for this convexification argument, which I will show next. Now we come to the more interesting parts of the talk, defining this curvature of sets, of a boundary of sets. So if we have, this will be now the setting for the remaining. If we have a locally compact RCT space with a variable lower Ricci bound and a closed subset which satisfies some conditions which avoid trivialities, we look on the distance function from this set, and we say that the boundary of the curvature is given by the convexity bound of this distance function. If you want to make your life easier, you also can take the signed distance function. This looks a little bit more smooth, but you measure this only outside, so it doesn't really matter how you define this function inside of y. So this will be our preliminary definition. It's a little bit improved. We say it's a lower bound for the curvature if for all epsilon this V is lambda minus epsilon convex, not only on the boundary, which would be a void definition, but in a neighborhood, in an outside neighborhood of a boundary. So if you have a boundary, you choose locally an epsilon neighborhood, and in this epsilon or delta neighborhood, depending on epsilon, this should be lambda convex in the sense of this standard definition of convexity, or lambda minus epsilon convex. Typical examples are, of course, closed subsets of Riemannian manifolds with smooth boundary, and this lower curvature bound coincides with a lower bound for the second fundamental form of curvature tensor. It also applies to more singular spaces, Alexandrov spaces with lower bounded curvature. To simplify presentation here, I assume curvature is bounded from below by 0, but actually this is also stated for any k. Assuming we have an exterior ball condition with maximal radius at a given point z, then this negative of 1 over this radius is a lower bound for the curvature of this boundary. So you have really this intuitive interpretation of this boundary, and this exactly is what you want to know. And this applies, as I mentioned, to spaces which are more singular, and it also applies to domains which are not regular. Of course, this also gives new insights if you do this in Riemannian cases. You also could think of sets which have quite some irregular structure. And the main theorem now here in this context is, if we have such a locally convex set with curvature bound lambda, then if we give a weight e to the minus lambda v up to epsilon, then we make this domain convex. And this is, of course, kind of core result here in this context. And again, I guess I should give at least a small sketch of how we prove it. Okay. Again, the question, is it readable if we do something here? Well, okay. So how do we prove this? So let's assume that our y is the complement of such a disk. And we want to make this, domain convex. So what we do is we give this weight function on this set, so, which makes transportation here inside more expensive. It's not singular, huh? It just starts linearly with a certain curve which comes from the curvature. And now the proof why this is convex is really quite nice. So what we have to prove is now that this y, the complement of this disk in this new metric, is convex. So what do? If we have a curve which goes through this set, then we apply gradient flow for this function in order to move these points until they reach the boundary. And we construct a new curve by stopping this gradient flow as soon as we are in this set y. And now there are two effects of this gradient flow, which combined ensure that the new curve is shorter than the old one. First of all, of course, here we see a certain expansion coming from the fact that it's a gradient flow from a non-convex function. But we measure the length in the new distance. So the old curve was measured with this disadvantage weight, so it was very expensive. And now we go outside, and the benefit is just balancing with the price of expanding the curve. So this new curve is now shorter than the old one. This proves the old one had no chance to be a geodesic in this new metric. And maybe I should also say that essentially the same argument applies if we are now, if our set y now is the disk, so we have this complement. Now we make a weight function which is constant 1 here and which grows linearly. And now again we can make a gradient flow. Now it would be an uphill gradient flow which guarantees that a curve which wants to leave y under the uphill gradient flow will be moved into y, and it does not enlarge the distance. So in some sense we make with this weight the set as less convex as possible, but it's still convex. So in some sense this picture is misleading. You should really think that these sets are made to half spaces. And for half spaces you would not see any improvement if you reflect them. Okay, and then there is actually a slightly modified definition. I do not want to stress this very much. Instead of requesting this for the lower bound and for the function v, we could and we will assume or allow that there are sequences of Vn and lambda n such that this Vn is lambda n convex, at least locally, and this Vn and lambda n, they should be sufficiently regular. Of course, our functions here, they are not that regular, yeah, because we have this kink inside, so we should at least think that it's extended and so on. But this is then on the technical side, we allow approximation in the F stands for the domain of a Dirichlet form, so it's a H1 space. So it's a rather moderate assumption. But for technical reasons, we need that these approximating functions are in domains of operators. Now what is time change? I already mentioned this a little bit. So with these functions displayed here, now we make the time change. So we change the measure in the standard way and the metric in this way, which amounts that we end up with a new Dirichlet form where, roughly speaking, the Dirichlet energy does not change. Of course, the domain changes, but let me leave out this question of changing of the domain. But for functions being in the domain of the old and new one, the energy is just the same. It's the same gradient. And okay, what is changing is the L2 structure, so only the measure changes. And in probabilistic terms, this means we have the same measure on paths, and we have the same trajectories, but you run with a different speed on them, therefore time change. Yeah, so there is an integral of this weight function with respect to Brownian motion integrated up, and the inverse of this is your new clock. And this explains this naming time change. And this is one of the basic transformations in Türchli-form theory, but it's still surprising to me that the fundamental result of the change of a Bernoulli-Emery constant and a time change is not derived in full generality. So I started this in the gamma calculus language some years ago. Then Bangchang extended this to metric measure spaces, but again with quite a number of restrictions. The point is, it should be true in this generality which is requested to state the result. And the previous assumptions used with test functions and so on, so 3 times differentiability and so forth. So what we now are aiming for is the following result. We want to start with a Bernoulli-Emery condition with a nice function k, let's say lower semi-continuous, lower bounded from below, a finite dimension, and we want to end up with whatever ugly object k kappa prime, measure or distribution or whatever, a number n prime, choose an arbitrary larger than n, and when we want to allow any weight function which is locally in the domain and continuous. Continuity we could even weaken, but then things are a little bit unreadable, so this formula would be destroyed and we would have to replace it by more complicated objects. And then the claim is, if we choose an arbitrary psi in the domain, we end up with this curvature bound. So we have an old curvature bound, we have a number times gradient psi squared, which is fine, and we have a distributional Laplacian of psi. So since psi is in H1, this is H minus 1. If psi is in the domain of an operator, of course this is a L2 function, or is a reasonable function, we can write it this way. But for later purpose, I want to formulate this really in this distributional way. I already told you, here we make a distribution, here we can assume a lot of smoothness. If we go back, this function, which looks like this one, is either not in the domain of an operator. Actually, we can modify it. We could replace this by a function which is nice here. So we take the sign distance function, then it's in the domain of an operator, but then it's not in the domain of a reflected Dirichlet form. So at one place you anyway have to pay the price. So for later use we need this distributional version. As I mentioned, if psi is in the domain of an operator, this is a function, and if this function is continuous, now comes again the Braun, Habermann, and Sturm result. We can switch from the Lagrangian, from the Eulerian to the Lagrangian picture, and we know the curvature dimension condition. And therefore, on this way, we have to take a rather reasonable psi, because we go this way, derive here first of all Bernoulli-Emery, then we want to have curvature dimension, and then we want to use the fact that curvature dimension is preserved under restriction to convex sets. So this is now this restriction stuff. What does restriction mean, or passing to the Neumann? It's a general construction. If we have a closed subset, which is the closure of its interior, and certain triviality excluded, then we define the reflected Dirichlet form just by taking functions which are locally in the domain of the interior, integrating on the interior of this set the gamma operator in the function squared, and this is then if this integral is finite, this is the domain, and the energy is just the integral of the gamma operator. Integrated on the interior, but since the boundary has no mass, you also can integrate it on the whole set. This is the abstract definition of a reflected heat semigroup or Neumann heat semigroup. This is a nice Dirichlet form. You have a reflected ground motion. So this is the object which is given. And it turns out that reflection and time change commute. So if you think of a measure and you restrict it first and give a weight to it, it amounts to the same than giving weight and restricting it, and the same for the distance. So in this respect, on the level of this metric measure space, you see that reflection and time change commute. So if we make this reflection and time change, it's clear that we end up with a correct object. And the time change, which amounts to a convexity of y, actually it's locally convex. Locally convex is for technical reasons. For instance, if you're on the torus, if a set is almost touching itself, it's only locally convex. But this is enough for us. So it's locally convex, so we can restrict it. So the curvature dimension condition from the ambient space is inherited by the restricted space. And again, this curvature dimension now implies a Bakry-Emery condition. Now we are in this picture. We come with here, this restriction produces the curvature dimension in the Laplacian sense. It implies a curvature dimension in Bakry-Emery sense. And now we are ready to make the re-time change or time rechange. We want to transform this set, which is with a strange metric and strange measure. We want to transform it back to the old one. And of course, we just want to take just minus psi in place of psi to get rid of all these weights. And as I mentioned, for the forward direction, we can assume that psi is good enough for everything, but then the psi will not be in the domain of Neumann Laplacian. Yeah, because domain of a Neumann Laplacian means that the gradient is 0. And the gradient is used essentially to make the domain convex. If a gradient would be 0, this would not help anything. So therefore, for this going back, we end up with a functional term which involves the contribution from the forward direction and the singular contribution from the backward direction. And in some sense, it's clear it cannot be a nice function because we know that there is no gradient estimate of a classical type. And now we play around a little bit. Okay, I should say this is now for one function which does the job. And of course, there are quite a number of functions. So for instance, these functions which would be in the domain would be the signed distance functions. And we could, what we think of is that we take functions which are kind of smooth truncations of a signed distance function. So in y, they should be close to 0. On the complement, they should have this effect which we need. But actually, for the final result, only the value of this function in y plays a role. And on the other hand, what is needed for the convexification is only the part on the complement of y. So what remains is only this piece which is needed in order to be in the domain. So what we do, we choose a sequence of such functions, and therefore I had this definition of this regular curvature bound. We think of sequences of functions, and this, I should emphasize, is the curvature bound for this object. It does not depend on the choice of psi. There is no psi showing up there anywhere, because I made the transformation psi minus psi. So the weight is m, the measure is m, the distance is d. Psi shows up only in this formula. So I simply can ask, can I find functions which satisfy this formula and which converge in some sense? And this is what we do. We choose these regular approximations, and we want that these functions psi n are smooth, and then they converge to what I want, namely negative curvature times distance function. And then, since this object is singular, of course this Laplacian will converge to a singular Laplacian of this limit function. There is a Neumann Laplacian of this guy, and then there is simply the difference between Laplacian and Neumann Laplacian. This is the curvature which finally pops up. And if it's written this way, this difference can be written as lambda times the Laplacian of this distance function, evaluated only in y. In y, the function is 0. So it's only the contribution on the boundary. So if this is really on the boundary, and I call this sigma surface measure. Actually, it requires some assumption that this surface measure, that this is really a distribution, but it's a distribution in all Riemannian, Alexandrov, and so forth cases. If we have a closed Riemann manifold which allows Green's formula, then it is really the surface measure. So Green's formula implies that this, the classical surface measure, is the Laplacian of a distance function in distributional sense. And now this is then the final result. Here are these technical assumptions. We choose functions which are nice enough to be in the domain of a Laplacian. And for Vn, they have to have gradient almost 1 on the boundary. They have to have the right convexity and so forth, and the convergence property. And then we end up with this curvature bound as a signed measure valued right-hand side of Bochner inequality. And this allows then to apply semi-group technique to deduce this term which I have already displayed in the beginning. This is this Feynman-Katz formula, taking into account the measure in the interior. But a similar formula also applies to this guy. And what we need to get hands on the sigma is the so-called additive functional corresponding to this measure, which intuitively means you integrate this measure along paths, which sounds a little bit impossible, but this is an old idea of Fukushima, that for instance for each function in the domain of a form, the distributional Laplacian is nice in the sense that you can integrate this distribution along paths. This is the Fukushima decomposition, and this is the kind of, it's not finite variation, it's bounded energy in Fukushima decomposition. So this is a well-defined object, and of course what you have to deal with is the Schrödinger semigroup with this right-hand side as measure, but also there is a well-established theory which allows to represent Schrödinger semigroups with measures as generalized potentials. Let me summarize once again this major tour which we made. So we start in the Lagrangian picture with an optimal transport curvature dimension condition. We pass to the Berkeley-Emery version, go in the Eulerian picture. Then we make the time change. For the time change, it's really much better to have this formal calculus with Bochner or gamma calculus. When we go back in the Lagrangian picture, because here we know that restriction to convex sets does not change anything. It would be nice if someone can tell me how to do this just in the Bochner formula. It should be possible, but I thought here's a hand raising. No, okay. I was always thinking that someone stands up and says it's much easier, go directly this way. At the moment, there is no direct way, as far as I understood, but it's certainly worth to think of this direct way. And here we have to go back again, switching these pictures from Lagrangian to Eulerian, and again time change, and now here we make the singular time change. The very last one is singular. We could already, in some sense, what would be tempting is to start from the very beginning with psi being this truncated function. But then the problem is already here we cannot make the switch between the two curvature dimensions, because at the moment there is no result which tells us that these two versions of curvature dimension are equivalent if the curvature bound is a measure. This is a program which we are working on, but at the moment this does not work. Okay, thanks for your attention.
Thank you very much for your lecture, which is open for discussion, additions of shortcuts, whatever. So please raise your hand.
Is the finite n assumption at the beginning on the dimension n must be finite, right?
Yeah, actually this is the crucial point for this time change result.
Okay.
Where's time change? Here. Yeah. So this time change result, in contrast to drift transformation. Drift transformation is a result which holds independent of dimension. This time change result requires that we start with a finite dimension and we have to increase the dimension. We can increase it by whatever small amount, but it's only true for finite dimension. And maybe therefore it's not that well studied. But instead of formulating this with metric measure space in the work with function, we will formulate it just as a Dirichlet form result. Dirichlet form result with curvature dimension, but it requires finite dimension. And therefore, the complete program requires finite dimension because we twice make this time change. And we lose twice a little bit of dimension. But this dimension in our case is multiplied by the gradient of this psi in the interior, which anyway we throw away in the end. So in some sense, our final result should be true without dimension, but or could be true. Should be more moderate. Could be true.
Any further questions or remarks? If this is not the case, we thank all the speakers of this morning once again. I wish all of you a nice afternoon. Enjoy the sun, enjoy the tower, and come back tomorrow morning at 9.